The ancient world was once as ordinary to its inhabitants as the modern world is to us. The cities were familiar, the monuments had names, the roads had destinations. People knew who built them and why they existed. Then centuries passed, civilizations collapsed, languages disappeared, and memories faded. What was once common knowledge slowly became mystery. Today, archaeologists often encounter the remains of places that were never intended to be mysterious at all. Yet the people who could explain them are long gone. We are left with fragments of their world, walls without stories, symbols without translations, and structures without certainty. The challenge of archaeology is not simply uncovering the past. It is trying to reconstruct meaning from pieces of a conversation that ended thousands of years ago. Kundzoros Cave City presents one of the most unusual engineering mysteries in the ancient world. Hidden within a deep canyon in the Unik province of southern Armenia, this vast settlement was carved directly into sandstone cliffs that rise above a rugged river valley. Unlike famous underground cities such as Cappadocia or monumental complexes such as Petra, Kundzoros developed as a vertical city suspended on canyon walls. Thousands of people lived here for centuries, yet many of the technologies that allowed such a settlement to function remain poorly understood. The site became known to archaeologists and historians through 19th century surveys and travel accounts, although local communities had inhabited the caves for generations. By the 19th century, records suggest that between 8,000 and 10,000 people lived throughout the canyon system. More than 1,800 cave dwellings may have existed at its peak. Even today, hundreds of artificial caves remain visible along the cliffs, preserving evidence of a remarkably complex society that somehow transformed a difficult landscape into a thriving urban environment. The first mystery concerns the sheer scale of excavation. Many visitors assume the caves are natural formations, but detailed examination reveals that a significant number were enlarged, modified, or entirely created by human labour. Entire rooms, storage chambers, stables, workshops, and religious spaces were carved into the canyon walls. Some chambers contain flat ceilings, straight walls, carved niches, and carefully shaped entrances. Archaeologists estimate that thousands of cubic meters of rock were removed during the settlement's development. This raises an important engineering question. How were these spaces excavated efficiently? Iron tools were available during much of the settlement's history, but even with metal implements, carving hundreds of large chambers into cliff faces would have required enormous labour investment. Experimental archaeology demonstrates that removing a single cubic metre of hard rock with traditional hand tools can require dozens of workdays. When multiplied across hundreds or even thousands of chambers, the total labour becomes staggering. Researchers still cannot determine precisely how construction projects were organised, how labour was coordinated, or how technical knowledge was transmitted across generations. The second mystery involves access and transportation. Many caves are positioned tens of metres above the canyon floor. Today, reaching some of them requires difficult climbing. Yet historical accounts describe a functioning city where families, livestock, food supplies and trade goods moved regularly between different parts of the settlement. Evidence suggests the existence of extensive wooden staircases, rope bridges, suspended walkways, and cliffside paths. Most of these structures disappeared long ago, leaving only fragments of anchoring points and carved access routes. The challenge for archaeologists is that the transportation network itself has largely vanished. What survives are the caves, but not the infrastructure that connected them. This situation resembles mysteries found at other archaeological sites. At Machu Picchu, researchers continue studying how steep mountain pathways supported large populations. At Petra, archaeologists investigate how movement was organised across complex terrain. Kundzuresk presents a similar puzzle. The difference is that much of its transportation system was likely constructed from wood, meaning crucial evidence decayed centuries ago. The third and perhaps most fascinating mystery concerns water management. Every successful settlement depends on reliable access to water. For a community numbering several thousand people, daily consumption would have reached tens of thousands of litres. Modern estimates suggest that even a modest pre-industrial population of 8,000 people would require at least 20,000 to 40,000 litres of water per day for drinking, cooking and basic domestic activities. The canyon contains springs and seasonal water sources, but many residential caves sit high above the valley floor. How water reached these elevated districts remains uncertain. Some researchers propose the use of storage cisterns that collected rainwater. Others suggest systems of manual transport using animals and containers. However, no surviving hydraulic infrastructure comparable to the aqueducts of Rome or the channels of Petra has been identified. This absence of evidence creates one of the greatest unanswered questions at Kundzuresk. The settlement clearly supported a substantial population, yet the logistical system that sustained that population remains largely invisible. Another mystery involves environmental engineering. Armenia experiences significant seasonal temperature variation. Winters can be severe, while summers can be hot and dry. Surprisingly, many caves maintain relatively stable internal temperatures throughout the year. Modern measurements in comparable rock-cut settlements show that underground or semi-underground chambers often remain near the average annual temperature of the surrounding region. Such thermal stability provides natural insulation against both heat and cold. However, achieving comfortable living conditions requires more than temperature control alone. Ventilation is equally important. Many Kundzuresk chambers contain openings positioned in ways that may have encouraged natural airflow. Some researchers suspect that builders understood how wind patterns move through the canyon and intentionally designed entrances to maximize ventilation while minimizing heat loss. If true, this would represent a sophisticated form of passive climate control developed centuries before modern environmental engineering. The fifth mystery concerns defense. Throughout history, southern Armenia occupied a strategic position between competing empires, kingdoms, and trade networks. The region experienced repeated conflicts involving Persians, Ottomans, Mongols, and various Armenian states. Despite this instability, Kundzuresk survived for centuries. Its location may explain why. Unlike conventional fortified cities protected by walls, Kundzuresk used geography as its primary defense system. Many entrances remain difficult to identify even today. Attackers approaching from the canyon floor would have faced steep cliffs, narrow access routes, and elevated observation points. Military historians often compare natural defensive systems with sites such as Cappadocia's underground cities or the cliff dwellings of Mesa Verde in North America. Yet, Kundzuresk may represent an even more extreme example of defensive architecture integrated directly into the landscape. Exactly how observation networks functioned, how warnings were transmitted, and how defensive positions were coordinated remains uncertain. The sixth mystery revolves around urban planning. At first glance, the settlement appears chaotic. Closer inspection suggests otherwise. Groups of caves seem organized into functional zones. Certain areas contain concentrations of storage facilities. Others contain evidence of domestic occupation. Religious structures appear in strategically important locations. This pattern suggests planning rather than random expansion. Yet no maps, engineering documents, or planning records survive. Researchers therefore face a difficult challenge. They can observe the final result but cannot reconstruct the decision-making process that created it. How were new caves assigned? Who authorized expansion projects? How are property boundaries determined? How was infrastructure maintained across a settlement extending through a vast canyon system? Such questions remain unanswered. Modern technology has revealed new information about the settlement. Archaeologists employ drone surveys, photogrammetry, laser scanning, geological analysis, and digital terrain modelling to map the canyon in unprecedented detail. These tools allow researchers to reconstruct portions of the ancient landscape and identify previously undocumented structures. Yet many of the most important questions remain unresolved. How was water distributed? How extensive was the transportation network? How were large-scale excavation projects organised? How much technical knowledge disappeared when the cave city was finally abandoned during the 20th century? Myrtos Pyrgos was a Bronze Age Minoan industrial centre located on the south coast of Crete, Greece. Nearly 4,000 years ago, this settlement produced, stored, and distributed goods on a scale that still surprises archaeologists today. The site was first excavated extensively by British archaeologist Gerald Cadogan beginning in the 1960s. Beneath layers of collapsed stone buildings, researchers uncovered workshops, storage facilities, industrial installations, and evidence of large-scale agricultural processing. What emerged was not a simple village, but something far more sophisticated, a production centre operating centuries before most of Europe developed comparable economic complexity. The greatest mystery of Myrtos Pyrgos is not its architecture or its age. It is the level of technological organisation achieved by people living during the Bronze Age. How did a society without iron tools, modern machinery, or written records that can be fully understood create what appears to have been an industrial economy? Most Bronze Age settlements in Europe were relatively small agricultural communities focused on local survival, yet Myrtos Pyrgos appears fundamentally different. Excavations revealed evidence for specialized production areas, storage facilities, administrative spaces, and manufacturing activities concentrated within a single settlement. Archaeologists identified workshops associated with food processing, textile production, and agricultural storage. This level of specialization resembles economic systems normally associated with much larger urban centers. Similar patterns are seen at major Minoan sites such as Knossos and Phaistos, yet Pyrgos was not a palace and lacked the monumental architecture usually associated with centralized authority. The question remains unanswered. Who coordinated all of this activity? Producing surplus goods requires planning, labor organization, transportation networks, and resource management. Yet the mechanisms behind these operations remain largely invisible because the administrative records of Minoan Crete remain undeciphered. The result is an archaeological paradox. We can see the products of a highly organized system, but we cannot fully understand the system itself. The most fascinating mystery at Myrtos Pyrgos involves olive oil production. Today, olive oil is often viewed as a simple agricultural product. In reality, producing high-quality oil at industrial scale requires an extraordinary understanding of timing, engineering, chemistry, and logistics. Archaeological evidence suggests that Pyrgos was deeply involved in olive processing during the Bronze Age. Storage facilities, large containers, processing installations, and agricultural remains all point towards significant production activity. This raises a remarkable question. How were Bronze Age people producing olive oil at a scale capable of supporting regional trade nearly 4,000 years ago? Modern olive oil production depends on carefully controlled procedures. Olives must be harvested at the correct stage of ripeness. Delays can reduce quality. Crushing must occur quickly. Separation of oil from water requires technical knowledge, and storage conditions must prevent oxidation and spoilage. Yet, evidence suggests that Minoan producers were successfully managing these challenges, long before the scientific principles involved were understood. Some of the storage jars discovered at Minoan sites across Crete, known as pithoi, could hold hundreds or even thousands of litres. Certain examples exceed 1.5 metres in height. Their presence indicates storage volumes far beyond the needs of individual households. The scale becomes even more impressive when compared with other contemporary societies. Around 2000 BC, much of Europe remained dominated by relatively small farming communities. Meanwhile, communities in Crete were already participating in maritime trade networks extending hundreds of kilometers across the eastern Mediterranean. Researchers estimate that olive trees require years before reaching productive maturity. Establishing large olive plantations therefore demanded long-term planning extending across generations. Such investments suggest sophisticated economic thinking rarely associated with prehistoric societies. Another puzzle concerns efficiency. Experimental archaeology has demonstrated that traditional stone presses can achieve surprisingly high extraction rates when operated by experienced workers. Some reconstructed systems recover substantial percentages of available oil despite their apparent simplicity. This raises the possibility that Minoan producers possessed practical engineering knowledge accumulated through centuries of experimentation. But exactly how efficient were their systems? Nobody knows. No complete pressing installation has survived in operational condition, and archaeologists must reconstruct the process from fragments, foundations, containers, and indirect evidence. The technology that powered one of the Mediterranean's earliest major export industries remains partly hidden. One of the most striking discoveries at Pyrgos is the scale of storage capacity. Large pithoi were found throughout the settlement. These enormous ceramic vessels required significant resources to manufacture. Producing a single jar involved collecting clay, preparing materials, shaping massive forms, controlling firing temperatures, and transport finished vessels without breaking them. Such containers were not created casually. Their presence suggests organized collection and redistribution of agricultural products. But what exactly was being stored? Olive oil is one possibility, wine is another. Grain, dried foods, and other trade commodities may also have been present. The mystery is not merely what the jars contained, but how inventory was managed. Without modern accounting systems, how did administrators track quantities moving through the settlement? The answer may once have existed in documents written in Linear A, the undeciphered script of the Minoans. Unfortunately, the script remains one of archaeology's greatest unsolved puzzles. Crete sits within one of the most active seismic regions in the Mediterranean. Over thousands of years, powerful earthquakes have repeatedly struck the island. Despite this danger, the builders of Pyrgos constructed substantial stone buildings, multiple room complexes, staircases, and structures that survived long enough to leave significant archaeological remains. This raises another engineering mystery. How much did Minoan builders understand about earthquake-resistant construction? Researchers studying Minoan architecture have noted features that may have helped structures absorb seismic stress. Flexible materials, timber reinforcements, carefully distributed weight, and strategic wall layouts appear repeatedly across Minoan sites. Whether these were intentional anti-earthquake technologies or fortunate architectural traditions remains debated. Either way, the results are remarkable. Many structures endured in a region where earthquakes regularly destroy modern buildings. The final mystery may be the most important. Myrtos Pyrgos clearly participated in a complex economy. Production occurred, goods were stored, trade took place, and labour was organised. Yet the administrative systems behind these activities remains largely invisible. Linear A inscriptions discovered across Crete demonstrate that the Minoans possessed a writing system. However, unlike Egyptian hieroglyphs or Mesopotamian cuneiform, Linear A has never been fully deciphered. As a result, we may be looking directly at records of Bronze Age production while being unable to read them. The ancient ruins of Paphos located on the southwest coast of Cyprus, preserve one of the greatest archaeological mysteries of the Roman world. How did ancient engineers and artists create masterpieces of such precision that they still challenge modern explanations nearly 2,000 years later? Systematic excavations began after a farmer accidentally uncovered part of a mosaic floor in 1962 near modern Paphos, leading archaeologists to reveal an entire buried Roman city filled with villas, tombs, theatres, and engineering works. The greatest mystery of Paphos lies beneath visitors' feet. Inside the House of Dionysus, House of Theseus, and House of Ion are some of the finest Roman mosaics ever discovered. Created between the 2nd and 4th centuries AD, these floors cover thousands of square meters and contain millions of tiny stone pieces known as tesserae. At first glance, they appear beautiful. Under scientific examination, they become puzzling. Many tesserae measure only a few millimeters across, yet the artist created smooth curves, realistic human anatomy, detailed facial expressions, and sophisticated shading effects that resemble painted artwork rather than stone construction. In some scenes, figures appear three-dimensional despite being composed entirely of coloured stones. The House of Dionysus alone contains approximately 2,000 square meters of mosaics. To maintain consistent proportions across such vast surfaces would require an extraordinary level of planning. Modern mosaic artists often rely on scaled drawings, projection methods, or digital templates. Roman craftsmen had none of these tools. Archaeologists believe master designers may have used geometric grids, string systems, and preliminary sketches. However, no complete design manuals have ever been found. The exact workflow remains unknown. The mystery becomes even greater when comparing Paphos with other famous Roman mosaic centres. Mosaics from sites in North Africa, such as those at El Gem Amphitheatre and nearby Roman villas, display exceptional quality, but many experts consider the finest works of Paphos equal or superior in complexity. Some scenes contain hundreds of individual figures arranged with remarkable mathematical balance. What remains unexplained is consistency. Different villas built decades apart exhibit nearly identical standards of craftsmanship. This suggests the existence of highly organized training systems or workshops whose methods disappeared without leaving written records. Modern researchers can identify pigments, stone sources, and construction layers using spectroscopy and microscopic analysis. Yet they still cannot fully reconstruct how ancient craftsmen coordinated thousands of design decisions with such precision over enormous surfaces. The mosaics survived earthquakes, invasions, weathering, and nearly 2 millennia of burial. Ironically, we understand the stones themselves better than the knowledge that assembled them. Cyprus sits near active tectonic zones where earthquakes have repeatedly devastated cities throughout history. Historical records describe major earthquakes striking the island in the 4th century AD, particularly around AD 332 and AD 365. Many ancient settlements were heavily damaged or destroyed. Yet, portions of Paphos endured. Excavations reveal that builders often combined different construction materials within the same structure. Rather than relying entirely on rigid stone blocks, they incorporated layers capable of distributing stress and absorbing vibration. Some foundations appear deliberately designed to reduce structural failure. Similar concepts can be seen in later earthquake-resistant architecture developed centuries afterward. The mystery is not that Roman engineers understood earthquakes. The mystery is how much they understood. Without seismographs, geological surveys, or modern engineering calculations, builders repeatedly created structures capable of surviving in a dangerous seismic environment. Their practical knowledge may have been based on centuries of observation, but the exact principles they applied remain uncertain. Ancient cities live or die by water. Unlike cities positioned along major rivers such as Alexandria on the Nile or Antioch on the Orontes, Paphos lacked access to a massive permanent river system. Nevertheless, it supported a substantial urban population for centuries. Archaeologists have uncovered reservoirs, cisterns, channels, wells, and distribution systems spread throughout the city. The engineering challenge was enormous. Water had to travel across varying terrain while maintaining carefully controlled gradients. Even slight errors could cause stagnation, overflow, or complete system failure. Surveys show that many Roman aqueduct systems throughout the empire operated with gradients measured in only a few centimeters per 100 meters. Comparable levels of precision appear within parts of the infrastructure serving Paphos. How ancient surveyors achieved such accuracy remains debated. Roman instruments such as the chorobates and groma are known from historical texts, but their practical limits are still discussed by engineers today. The water system demonstrates that Paphos was not merely a collection of buildings. It functioned as a carefully managed machine. Few locations in Cyprus are more enigmatic than the tombs of the kings. Despite the name, most of the individuals buried there were likely elite officials and aristocrats, rather than actual kings. Carved directly into solid limestone between the 3rd century BC and 1st century AD, these tombs resemble underground palaces. Many contain courtyards, columns, chambers, and symmetrical layouts. Creating such structures required removing thousands of tons of rock. Unlike building upward, excavation offers little room for error. A mistake in alignment can ruin an entire project. Yet many tomb complexes display remarkable geometric precision. Columns align accurately with surrounding walls, while courtyards maintain carefully planned proportions. Researchers still debate how ancient builders established reference points underground, while preserving symmetry across large excavated spaces. The challenge resembles that faced by the creators of Petra in Jordan and the rock-cut monuments of Egypt, yet many technical details remain unknown. Excavations have revealed evidence of a highly organized city. Roads, villas, public buildings, markets, baths, and administrative structures were integrated into a coherent urban framework. The House of Theseus alone covers roughly 9,000 square meters, making it one of the largest Roman residences discovered in the Eastern Mediterranean. Managing a city of this scale required surveying, logistics, taxation, labor coordination, material transport, and long-term planning. The Roman Empire certainly possessed administrative expertise. What remains mysterious is how local engineers translated imperial concepts into functioning urban systems adapted specifically to Cyprus. No complete planning documents survive. The city itself is the only remaining blueprint. Perhaps the greatest mystery of Paphos is not what survives, but what vanished. Modern archaeology employs satellite imaging, laser scanning, ground-penetrating radar, digital modeling, chemical analysis, and artificial intelligence. These technologies allow researchers to study ancient structures in unprecedented detail. Yet despite all these tools, many practical aspects of construction remain hidden. How were mosaic masters trained? How were enormous projects coordinated? How did surveyors achieve such remarkable precision? How were engineering techniques transmitted across generations? The answers disappeared long ago. If archaeologists could recover one lost secret from Paphos, would you choose the technique behind its perfect mosaics, or the engineering knowledge that kept the city functioning for centuries? Roman mass grave is a term used for a collection of mass burial sites discovered across the former Roman world, from York in Britain to Calcrease in Germany. Thousands of skeletons have been uncovered from these graves, revealing not only how people died, but also how the Roman Empire managed warfare, medicine, logistics, and engineering on a remarkable scale. The greatest mystery is not the deaths themselves, but the level of technological and organizational sophistication hidden beneath the bones. Many Roman mass graves were discovered by accident. Construction projects, road expansions, and archaeological excavations revealed large groups of human remains buried together. One of the most significant discoveries was made at Driffield Terrace in York, England, where archaeologists uncovered more than 80 decapitated male skeletons between 2004 and 2005. Other major findings came from the Kalkreis battlefield in Germany, which is widely linked to the Battle of the Teutoburg Forest in AD 9, where thousands of Roman soldiers were defeated by Germanic tribes. These sites turned scattered historical records into tangible archaeological evidence. The first mystery involves the remarkable efficiency with which the Romans handled mass casualties. Ancient historians described battles involving tens of thousands of soldiers. The Battle of Cannae in 216 BC reportedly resulted in more than 50 seal-zone Roman deaths in a single day. Even if ancient estimates were exaggerated, the scale of casualties was enormous. Yet archaeological evidence often shows bodies arranged in organized layers rather than dumped randomly. This suggests that Roman forces possessed highly structured procedures for collecting, transporting, identifying, and burying the dead. Without trucks, cranes, or modern machinery, moving thousands of bodies after a battle would have required extraordinary coordination. Historians understand parts of the Roman military machine, but the exact logistics behind large-scale battlefield recovery operations remain unclear. The second, and perhaps most fascinating mystery concerns battlefield surgery. Roman mass graves preserve direct evidence of medical procedures that seem surprisingly advanced for an ancient civilization. Numerous skeletons recovered from military cemeteries display signs of healed amputations, repaired fractures, and surgical interventions. Some skulls contain evidence of trepanation, a procedure involving the deliberate drilling or cutting of the skull. Other remains show clean amputations of arms or legs where the bone surface indicates that the patient survived long enough for healing to occur. In several cases, bones reveal smooth regrowth around surgical cuts, demonstrating that the operation was successful. This presents a major puzzle. The Roman Empire had no knowledge of bacteria, no antibiotics, and no modern anesthesia. Yet some patients survived procedures that would remain highly dangerous even centuries later. Military doctors known as medici served Roman legions, and archaeological discoveries have revealed sophisticated surgical instruments including scalpels, forceps, probes, hooks, catheters, and specialized bone-cutting tools. Some Roman scalpels were manufactured from steel and remain recognizable to modern surgeons. The mystery is not whether Roman surgery existed. The mystery is how effective it was. Experimental studies suggest that severe infections should have killed many patients following major surgery. Yet skeletal evidence repeatedly demonstrates survival after operations. Roman medical texts describe the use of wine, vinegar, honey, and herbal compounds during treatment. Modern science has confirmed that honey possesses antibacterial properties and that wine can act as a mild antiseptic. However, researchers still debate whether these methods alone can explain the survival rates implied by the archaeological evidence. Comparisons with later history make the puzzle even more striking. During the Napoleonic Wars in the early 19th century, battlefield infections remained one of the leading causes of death, despite advances in medical knowledge. During the American Civil War, infection killed countless wounded soldiers. In some circumstances, Roman military medicine appears surprisingly competitive, with systems developed nearly 2,000 years later. Another unanswered question concerns training. The Roman army maintained approximately 25 to 30 legions during the imperial period, representing more than 150,000 legionaries, not including auxiliaries. Supporting such forces required hundreds of medical personnel distributed across vast distances. How standardized was their medical education? How were surgical techniques transmitted throughout the empire? Archaeologists continue to search for answers. The third mystery involves weapon technology revealed through skeletal trauma. Roman mass graves function almost like forensic laboratories frozen in time. Researchers can analyze wounds and reconstruct how soldiers died. Many skulls contain deep, narrow cuts consistent with blows from Roman swords. Others show puncture wounds produced by spears or pilum javelins. At Calcarees, investigators documented injuries that suggest highly disciplined combat techniques. Patterns of trauma often repeat across numerous skeletons, indicating standardized military training and standardized weapons. The Roman gladius was typically around 60 centimeters long and optimized for thrusting attacks. Ancient writers described Roman soldiers targeting vulnerable areas with remarkable precision. Skeletal evidence supports these accounts. The consistency of wounds raises questions about how Roman manufacturers maintained weapon quality across an empire stretching more than 5 million square kilometers at its peak. The fourth mystery concerns supply networks. Every mass grave represents the remains of soldiers who belong to a much larger military system. A single legion usually consisted of approximately 5,000 to 6,000 men. Feeding such a force required enormous quantities of grain, meat, water, equipment, and medical supplies. Historical estimates suggest that a legion could consume several tons of food every day. Yet Roman armies operated across deserts, mountains, forests, and frontier regions. Isotopic analysis of skeletal remains provides additional clues. Chemical signatures preserved within teeth and bones reveal where individuals grew up and what they ate. Studies have shown that soldiers buried together sometimes originated from entirely different regions of the empire. Men from North Africa, the Balkans, Gaul, Britain, and the Near East could serve in the same military structure. Managing such diversity required sophisticated administration. Payroll records, supply inventories, transport schedules, recruitment systems, and medical support networks had to function across thousands of kilometers. The physical remains demonstrate that the system worked. The exact mechanisms behind that success remain partly hidden. The fifth mystery involves identification and memory. Ancient battlefields were chaotic environments, yet Roman forces often returned years later to recover remains. The Roman historian Tacitus described how Germanicus revisited the site of the Teutoburg disaster around 6 years after the battle and ordered the burial of Roman bones still scattered across the landscape. The remarkable question is how those locations were remembered. Without satellite imagery, aerial surveys, or modern mapping systems, Roman commanders maintained knowledge of battlefield positions over long periods. Archaeological evidence suggests that many burial locations were carefully marked and organized. Wooden markers have long since vanished, but burial patterns indicate deliberate planning. This hints at a level of military record-keeping that exceeds what survives in written sources. The greatest mystery may be Rome's ability to combine medicine, engineering, logistics, administration, and military science into one efficient system. These mass graves reveal an empire that could recruit, equip, transport, and care for soldiers across vast distances for centuries. The skeletons are silent evidence of this achievement, yet much of the knowledge behind this system disappeared after the fall of the Western Roman Empire, leaving only the remains while the full organizational structure was lost. Bylany, in central Bohemia near Kutná Hora in the Czech Republic, preserves evidence of a farming society that achieved levels of organization and productivity thousands of years before metal tools, writing, or states existed. The site was identified through archaeological investigations beginning in 1953 under Czech archaeologist Bohumil Sudsky. Excavations eventually revealed one of the largest known settlements of the linear pottery culture, or LBK, dating to approximately 5500 to 4900 BC. What archaeologists discovered was not simply a prehistoric village. It was a landscape filled with longhouses, storage pits, agricultural evidence, and signs of a surprisingly advanced farming economy. More than 70 years after its discovery, Bylany continues to raise questions about how some of Europe's earliest farmers achieved results that appear difficult to explain with the technology they possessed. The most visible feature of Bylany is its collection of Neolithic longhouses. Archaeologists have identified traces of more than 100 structures, many measuring between 20 and 40 meters in length, with some approaching 45 meters. Building projects of this scale would have required thousands of wooden posts, massive roof frameworks, and careful engineering. Yet the inhabitants possessed no iron axes, steel saws, or advanced lifting equipment. Their primary tools were polished stone axes, flint blades, and wooden implements. Experimental archaeology has demonstrated that felling a mature oak tree using a polished stone axe can require several hours of continuous work. A single longhouse may have consumed hundreds of large timbers, making the labor investment enormous. The mystery is not merely how one house was built, but how dozens were constructed, maintained, replaced, and expanded over generations. Similar longhouses appear throughout LBK settlements across Central Europe, but Beleni provides one of the clearest examples of a community capable of organizing large-scale construction without written planning systems. Another puzzle emerges from the arrangement of the settlement itself. The longhouses were not scattered randomly across the landscape. Many shared similar orientations and were grouped in recognizable patterns, suggesting that the inhabitants followed rules regarding space, construction, and community organization. No maps have survived, no writing existed, and no measuring instruments have been recovered. Yet the settlement demonstrates a degree of planning unexpected for such an early farming society. Some researchers have proposed that standardized measurements based on ropes, body units, or inherited construction traditions may have existed. However, direct evidence remains absent. The result is a strange contradiction, a community that appears highly organized, but leaves no written explanation of how that organization functioned. When the first LBK farmers arrived in Central Europe, much of the region was covered by dense temperate forest. Creating the agricultural landscape visible at Beleni required clearing enormous areas of woodland. Trees had to be cut, roots removed, fields prepared, and grazing land established for livestock. Pollen studies indicate significant environmental transformation. During the Neolithic period, entire sections of natural forest disappeared and were replaced by human-managed landscapes. What remains difficult to understand is the speed at which this transformation occurred. Modern forestry machinery can clear land rapidly, but Neolithic farmers possessed only stone tools. Compared with other prehistoric societies, the scale of environmental modification at Beleni suggests a level of labor organization that continues to surprise researchers. This may be the greatest mystery of all. Agriculture arrived in Central Europe around 5500 BC with the expansion of LBK communities. The crops cultivated at Beleni included einkorn wheat, emmer wheat, barley, peas, and lentils, while livestock included cattle, pigs, sheep, and goats. At first glance, the system appears simple, yet the archaeological evidence suggests something far more sophisticated. The settlement remained occupied for centuries, new houses replaced older ones, populations persisted, and food supplies remained sufficiently stable to support construction projects, animal husbandry, and long-distance exchange networks. This creates a major scientific problem. Ancient agriculture is typically vulnerable to soil exhaustion because continuous cultivation removes nutrients such as nitrogen, phosphorus, and potassium from the ground. In many traditional farming systems, yields decline after repeated harvests unless fertility is restored. The question therefore becomes obvious. How did Neolithic farmers maintain productive fields generation after generation without modern fertilizers? Archaeologists have proposed several explanations. One possibility involves extensive manuring. Chemical analyses from other LBK sites have revealed isotopic signatures suggesting that animal manure may have been systematically applied to crops. If similar practices occurred at Beleni, these farmers may have understood soil fertility management far earlier than once believed. Another possibility is rotational farming. Rather than cultivating the same plots continuously, farmers may have shifted cultivation areas while allowing exhausted land to recover naturally. A third hypothesis involves mixed farming systems in which livestock and agriculture operated together in a highly integrated cycle. Animals provided manure, crop residues fed animals, and nutrients circulated throughout the settlement economy. What makes the mystery especially fascinating is comparison with later historical societies. Many medieval European communities struggled with declining yields and periodic famines, despite possessing iron tools, ploughs, and more advanced technologies. Yet Bellini's inhabitants appear to have sustained agricultural production for centuries, using little more than stone, tools, and accumulated ecological knowledge. Researchers studying LBK agriculture have estimated that wheat yields may have ranged from approximately 500 to 1,500 kilograms per hectare, depending on environmental conditions. Although modest by modern standards, such productivity would have been sufficient to support substantial populations if managed effectively. The challenge is that we still do not know exactly how they achieved this consistency. No written manuals exist, no farming records survive, and the knowledge disappeared thousands of years ago. All that remains are traces in the soil. Artifacts discovered at Bellini reveal connections extending far beyond the settlement itself. Geochemical analyses show that some stone materials originated hundreds of kilometers away, and certain flints likely came from southern Poland and other distant regions of Central Europe. This indicates the existence of exchange networks spanning remarkable distances. The mystery is logistical. There were no paved roads, no wagons on an industrial scale, and no states managing transportation. Yet valuable materials consistently moved across large territories. The situation resembles an early version of the exchange systems that would later characterize Bronze Age Europe, except that Bellini predates those networks by thousands of years. Excavations have uncovered thousands of pits scattered throughout the settlement. Some were originally dug to obtain clay for construction, while others became storage facilities, waste deposits, or locations for ritual activities. Several contain unusual combinations of artifacts, animal bones, and domestic refuse. Some appear carefully filled, while others seem deliberately abandoned. Despite decades of excavation, archaeologists still debate their exact functions. Were they storage facilities, ritual spaces, or markers of ownership? The evidence supports multiple interpretations, but no single explanation accounts for all examples. Templo Mayor was the most sacred structure of the Aztec capital of Tenochtitlan. Hidden beneath the center of present-day Mexico City, one of the largest modern cities on Earth, lie the remains of a temple complex that may preserve evidence of engineering, astronomy, and construction knowledge that researchers are still trying to fully understand. The modern discovery of Templo Mayor began in 1978 when electrical workers accidentally uncovered a massive stone disc depicting the Aztec goddess Coyolxauhqui. The find triggered one of the largest archaeological excavations in Mexican history. Archaeologists soon revealed that beneath the streets of Mexico City were the remains of the ceremonial heart of an empire that ruled millions of people before the Spanish conquest in 1521. One of the first mysteries concerns the location itself. Tenochtitlan was built on an island in Lake Texcoco, a shallow lake system in the Valley of Mexico. Modern engineers struggle with the same unstable ground today. Mexico City sinks by as much as 30 to 50 centimeters per year in some areas because of groundwater extraction. Yet the Aztecs managed to construct massive pyramids, plazas, palaces, and causeways on terrain that should have presented enormous structural challenges. Excavations have shown that Templo Mayor underwent at least 7 major construction phases between approximately 1325 and 1521. Each new version was built directly over the previous one, creating a giant architectural sequence similar to Russian nesting dolls. The largest phase reached an estimated height of around 45 meters. What puzzles researchers is how generations of builders maintained geometric consistency across centuries of expansion. Without surviving architectural plans, modern scholars can only speculate about the methods used to preserve alignment and symmetry over such a long period. The second mystery involves logistics. Archaeologists have recovered more than 200 ritual offerings containing thousands of objects from across Mesoamerica. These include jade from Guatemala, marine shells from both the Pacific Ocean and the Gulf of Mexico, coral, obsidian, jaguar remains, crocodile bones, eagle skeletons, and exotic fish species. Some materials travelled over 1,000 kilometres before reaching Tenochtitlan. Managing such a supply network would have required sophisticated organisation. Unlike the Roman Empire, which relied heavily on wheeled transport and draft animals, the Aztecs possessed neither. Goods were carried by human porters known as tamimis or transported by canoe through extensive waterway networks. How this system consistently delivered rare materials from distant regions remains one of the most impressive logistical achievements of the pre-Columbian world. The third and perhaps most fascinating mystery involves astronomy. Many researchers believe Templo Mayor functioned as a giant astronomical instrument integrated into the religious and political life of the Aztec Empire. The temple's twin shrines were dedicated to Tlaloc, the rain god, and Huitzilopochtli, the sun and war god. Their positioning appears to have been carefully planned, rather than chosen at random. Studies conducted during the 20th and 21st centuries identified potential alignments between the temple and significant solar events. Researchers observed that on certain dates associated with the agricultural calendar, the rising sun appeared between key architectural features of the complex. These observations would have helped priests determine the timing of planting seasons, religious ceremonies, and state rituals. The precision of these alignments raises difficult questions. The Aztecs had no telescopes, no optical instruments, and no written mathematical treatises comparable to those of ancient Greece. Yet they developed a calendar system accurate enough to coordinate ceremonies across a vast empire. Some archaeoastronomers have suggested that centuries of systematic sky observation allowed Aztec priests to track solar movement with remarkable accuracy. The sun's position on the horizon changes throughout the year. By recording these changes over generations, it would have been possible to establish highly reliable observational markers. However, there is still debate regarding how precise these alignments truly were. Some researchers argue that the observed astronomical connections are intentional and represent advanced observational science. Others caution that certain alignments may be partly coincidental. The controversy remains unresolved. The mystery becomes even deeper when Templo Mayor is compared with other ancient astronomical centres. Stonehenge in England tracks solstitial sunrise positions. The pyramids of Giza display extraordinary cardinal orientation. The Maya city of Chichen Itza incorporates solar shadow effects during equinoxes. Templo Mayor appears to belong within this global tradition of monumental architecture connected to celestial observation. Yet, unlike Stonehenge or Giza, Templo Mayor existed within a densely populated urban environment. Its astronomical functions had to coexist with political administration, military ceremonies, religious festivals, and daily life. This combination of practical urban planning and celestial alignment makes the site especially intriguing. Another mystery concerns the temple's hydraulic engineering. Tenochtitlan depended on an elaborate network of canals, dikes, aqueducts, and artificial agricultural islands known as chinampas. Historical accounts describe a city crossed by waterways, resembling Venice. The challenge was not merely bringing water into the city, but controlling it. Lake Texcoco contained brackish water, while much of the city's population required fresh water. The famous dike attributed to the ruler Nezahualcóyotl reportedly stretched for approximately 16 kilometers and helped separate saline and freshwater zones. Maintaining such infrastructure required knowledge of hydrology that archaeologists are still attempting to reconstruct. Templo Mayor itself reveals evidence of drainage systems designed to protect ceremonial areas from flooding. Given the unstable lake environment, even minor engineering errors could have produced catastrophic structural damage. Yet the temple survived repeated enlargements for nearly 2 centuries. The fifth mystery involves obsidian technology. Obsidian is volcanic glass formed by rapidly cooled lava. Microscopic analysis has demonstrated that obsidian blades can possess cutting edges significantly sharper than modern surgical steel. Numerous obsidian knives recovered from Templo Mayor exhibit extraordinary craftsmanship. Producing these tools required precise control over fracture mechanics. Unlike metal, obsidian cannot be forged or reshaped after breaking. A single mistake could ruin an entire blade. The consistency observed among many excavated specimens suggests the existence of highly specialized craftsmen with extensive technical knowledge. Another unanswered question concerns the enormous stone monuments associated with the temple. The famous Koyalzauki stone measures more than 3 meters in diameter and weighs several tons. Transporting such objects through an island city without wheeled vehicles remains difficult to explain in detail. Archaeologists generally believe that teams of laborers, ropes, wooden rollers, and ramps were used. However, no direct descriptions of the exact procedures survive. As a result, many aspects of Aztec heavy construction remain theoretical. The final mystery is not a single technology, but an entire system of knowledge that vanished after the Spanish conquest. When Hernán Cortés entered Tenochtitlan in 1519, the city may have contained between 200,000 and 300,000 inhabitants, making it comparable to or larger than many European capitals of the period. Within just a few years, war, disease, and colonial reconstruction transformed the city. Temples were demolished, records were destroyed, and generations of specialized knowledge disappeared. The physical remains survived underground, but much of the intellectual framework that created them was lost forever. Mulpir is an Iron Age hill fort in the Little Carpathian Mountains of western Slovakia that may preserve evidence of technologies far more advanced than historians expect from a small European community over 2,600 years ago. The site was discovered through archaeological investigations near the village of Smolenice during the 20th century, with major excavations conducted by Slovak archaeologists beginning in the 1960s. What emerged from the mountain was not a simple settlement, but a heavily fortified complex filled with evidence of sophisticated engineering, large-scale metallurgy, violent destruction, and technological capabilities that remain difficult to fully explain. The first mystery concerns the construction of the fortifications themselves. Mulpir occupies a steep hill, rising more than 400 meters above sea level, and building a settlement in such terrain required enormous logistical planning. Archaeologists identified multiple defensive walls built from stone and timber, forming a complex system that followed the contours of the mountain. Thousands of tons of material had to be transported uphill without wheeled machinery, cranes, or advanced lifting devices. The engineering challenge becomes clearer when compared to other Iron Age sites. At Biskupin in Poland, one of Europe's most famous fortified settlements, builders relied heavily on timber because transporting large quantities of stone was difficult. At Hüneberg in southern Germany, another major Iron Age centre, construction required extensive labour organisation and long-distance resource management. Mulpir appears to have achieved a similar level of complexity despite being located in rugged mountainous terrain. Researchers estimate that constructing the defensive system would have required the coordinated effort of hundreds of workers over many years. Yet no written records survive to explain how such a relatively small community organised labour on this scale. The administrative knowledge behind the project remains largely invisible. The second mystery involves the unusual destruction of the site. Excavations revealed extensive evidence of intense fire. Burned structures, collapsed walls, and layers of ash suggest a catastrophic event occurred sometime during the 6th century BCE. However, the temperatures reached during the destruction appear unusually high. Some stones within the fortifications display signs of thermal alteration. Similar phenomena have been documented at so-called vitrified forts in Scotland and parts of France, where temperatures exceeding 0 degrees Celsius may have partially altered the mineral structure of stone. Ordinary house fires rarely reach such temperatures over large areas. The question remains unresolved. Was Moulpir destroyed by invaders using large-scale incendiary attacks? Did defenders intentionally burn sections of the fortification, or did the inhabitants themselves destroy parts of the settlement during a ritual abandonment? Archaeologists continue to debate the answer. The third mystery concerns social organization. Moulpir was not simply a military outpost. Excavations revealed residential buildings, workshops, storage areas, and ritual spaces. This suggests a permanent population capable of supporting specialized craftsmen, religious activities, and long-term economic production. For a settlement operating around 600 BCE, such complexity raises important questions. Managing food supplies, construction projects, defense systems, and craft production required coordination that resembles the early stages of urban administration. Yet unlike the great cities of Mesopotamia or Egypt, Moulpir left no written archives. The mechanisms that allowed the community to function remain hidden from history. The fourth mystery involves evidence of ritual behavior and human sacrifice. Several human remains discovered at the site were found under unusual circumstances. Some skeletons were not buried according to standard funerary practices, while others appeared in locations associated with destruction layers or ritual spaces. Archaeologists have proposed various interpretations. Some individuals may have been victims of warfare, while others may have participated in ceremonies connected to religious practices. Few researchers have suggested the possibility of ritual sacrifice, although direct evidence remains limited. What makes the finds particularly intriguing is their similarity to discoveries from Celtic sanctuaries elsewhere in Europe, where human remains occasionally appear in ritual contexts. Whether Moulpir represents a local tradition or part of a broader Iron Age religious system remains uncertain. The fifth mystery, and perhaps the most extraordinary of all, is the advanced metallurgical technology practiced at Moulpir. Among the most significant discoveries at the site are evidence of iron production, metalworking waste, slag deposits, furnaces, and finished metal artifacts. These finds indicate that Moulpir was not merely consuming metal imported from elsewhere, it was actively producing and processing it. To modern observers, ironworking may appear straightforward, but in reality, Iron Age metallurgy was one of the most technologically demanding activities of the ancient world. Producing usable iron required controlling temperatures approaching 200 degrees Celsius inside furnaces fueled by charcoal. Craftsmen had to regulate airflow, maintain stable combustion conditions, select appropriate ores, and manage chemical reactions occurring inside the furnace. Small mistakes could ruin an entire production cycle. Modern experimental archaeology demonstrates how difficult this process actually is. Reconstructing Iron Age bloomery furnaces often requires repeated attempts before obtaining high-quality iron, and even slight variations in temperature or oxygen levels can dramatically affect results. Yet the metal workers of Moulpir appear to have mastered these techniques more than 2,600 years ago. Chemical analyses of slag recovered from the site suggest a surprisingly efficient production process. Researchers identified evidence that workers understood how to separate metallic iron from impurities while maximizing output from available ore. Such efficiency implies generations of accumulated technical knowledge. The scale of production creates an even greater mystery. Moulpir sits within a region containing valuable mineral resources, but transforming raw ore into tools and weapons required an entire industrial chain. Ore had to be mined, charcoal had to be produced from vast quantities of timber, furnaces had to be constructed and maintained, and skilled specialists had to oversee every stage. A single bloomery furnace could consume hundreds of kilograms of charcoal during operation. Experimental studies indicate that producing 1 kilogram of iron often required multiple kilograms of charcoal and significant amounts of ore. Sustaining continuous metal production therefore demanded careful management of natural resources. Where did this knowledge originate? Some scholars believe technological influences arrived through trade networks connecting Central Europe with the Hallstatt cultural sphere. Others argue that local craftsmen developed unique innovations adapted to regional conditions. Neither explanation fully accounts for the sophistication visible in the archaeological record. The mystery becomes even deeper when comparisons are made with neighbouring communities. Many contemporary settlements possessed iron objects, but relatively few show evidence for such extensive production activity. Mulpir appears to have functioned as a regional technological centre, concentrating expertise that exceeded what might be expected from its population size. The sixth mystery concerns long-distance connections. Artifacts recovered from Mulpir indicate participation in trade networks extending far beyond the Little Carpathians. Imported goods, exotic materials and stylistic influences suggest contact with distant regions of Central Europe. These connections likely facilitated the movement of ideas as well as objects. Metallurgical techniques, construction methods, and religious concepts may all have travelled through the same networks. Yet, archaeologists still cannot reconstruct the full extent of these interactions. The routes through which knowledge moved remain largely speculative. The final mystery is the disappearance of the settlement. Despite its strategic location, advanced defences and technological capabilities, Mulpir was eventually abandoned. The reasons remain uncertain. Warfare, political instability, economic disruption, environmental pressures, or shifts in trade routes have all been proposed. No single explanation accounts for all available evidence. Lubicza Królewska is an archaeological site in southeastern Poland, near the modern border with Ukraine. Beneath its quiet farmland lies evidence of communities that developed surprisingly advanced technologies thousands of years before writing reached this part of Europe. The site came to wider archaeological attention through systematic excavations and surveys that revealed settlements associated with Neolithic and early Bronze Age cultures, including funnel beaker and corded ware communities. What researchers uncovered was not a lost city or monumental temple. Instead, they found something that may be even more mysterious. Evidence of technological knowledge that should have been difficult for small farming societies to develop, preserve, and transmit over centuries. The first mystery involves the construction of large timber buildings. Archaeologists identified post holes indicating the existence of longhouses stretching more than 30 meters in length. Such structures required hundreds of trees and thousands of hours of labor. Experimental archaeology projects conducted in Central Europe have shown that felling a single mature oak using polished stone axes can require hours of continuous work. Building an entire settlement would therefore have demanded a level of organization that seems surprisingly sophisticated for communities without writing, centralized governments, or metal tools. Researchers still debate how these projects were coordinated. Did village leaders organize labor through social authority? Were construction techniques shared between distant communities? Or did specialized builders travel across regions carrying technical knowledge with them? The archaeological evidence remains incomplete. The second mystery concerns settlement planning. Surveys reveal that many structures appear to follow consistent orientations. This may seem insignificant today, but maintaining directional accuracy across multiple generations requires some method of measurement. Without compasses or formal surveying instruments, the inhabitants may have relied on solar observations, landscape markers, or inherited construction traditions. Similar questions have emerged at sites such as Çatalhöyük in Turkey and Skara Brae in Scotland, where surprisingly organized layouts challenge assumptions about early farming societies. The third mystery is perhaps the most fascinating of all: the underground storage pits and food preservation systems discovered throughout the settlement. At first glance, these pits appear simple. They are merely excavated holes in the ground. Yet, closer examination suggests that they may represent one of the most important technological achievements of prehistoric Europe. For early agricultural communities, food storage was a matter of survival. Harvests occurred only once per year, but people needed food every day. A failed storage system could mean famine, disease, and social collapse during winter. Many of the pits found at Libica Królewska display recurring shapes and dimensions, suggesting that their builders followed established design principles. Archaeologists have long noted that underground storage pits can create remarkably stable environmental conditions. Soil acts as a natural insulator, reducing temperature fluctuations compared with surface structures. Modern studies of underground grain storage have demonstrated that temperatures several feet below ground remain significantly more stable throughout the year. In parts of Europe, subsurface temperatures often fluctuate only a few degrees despite large seasonal changes above ground. Such stability slows spoilage and helps protect stored crops. The mystery is how Neolithic communities discovered these principles. Nobody recorded the experiments. No written manuals survive. Yet the evidence suggests that people understood how depth, shape, soil composition, drainage, and ventilation influenced preservation. Some pits appear deliberately positioned in locations with favorable drainage conditions. Others may have incorporated organic linings or coverings that improved storage performance. Researchers continue to investigate exactly how these systems functioned. The challenge becomes even more intriguing when compared with other ancient civilizations. In ancient Egypt, grain was stored in massive state-controlled granaries. In Mesopotamia, written records documented agricultural inventories. At Libica Królewska, however, similar storage goals were achieved without bureaucracies, writing systems, or monumental architecture. The technology itself was invisible. Unlike pyramids or temples, underground storage systems leave few traces behind, yet they may have been equally important to survival. A village capable of preserving grain through harsh winters could support larger populations, withstand poor harvests, and invest labor into construction, trade, and craft production. Some researchers argue that food storage technologies may have played a role in the rise of social complexity across prehistoric Europe. Communities capable of producing and preserving surplus resources gained advantages over neighboring groups. If this interpretation is correct, the humble storage pits at Libica Królewska may represent an early form of agricultural engineering that helped transform European society. Even today, archaeologists cannot fully reconstruct the knowledge behind these systems. We can measure the pits, we can analyze pollen and plant remains, we can estimate storage capacity, but we still do not know exactly how generations of farmers refined these designs without written science. The fourth mystery involves long-distance exchange networks. Stone tools recovered at the site reveal that some raw materials originated far from the settlement itself. High-quality flint often traveled hundreds of kilometers across Central Europe. Such movement required routes, partnerships, and communication between distant communities. This creates a logistical puzzle. Transporting valuable stone across large distances without roads, carts, or organized states demanded considerable planning. Similar exchange networks have been documented throughout Neolithic Europe, but many details remain unknown. How did traders navigate? How was trust maintained between communities that may never have met before? What mechanisms protected valuable resources during transport? Archaeologists continue searching for answers. The fifth mystery concerns the remarkable precision of flint craftsmanship. Many recovered blades demonstrate extraordinary skill. Producing long, thin cutting edges from brittle stone requires precise control of force and angle. Modern experimental knappers often spend years mastering techniques that prehistoric artisans performed routinely. The existence of such expertise suggests specialized training, yet there is no evidence of schools, manuals, or written instruction. Knowledge must have been transmitted directly from person to person across generations. How this technical education functioned remains uncertain. Located in Mérida, Extremadura, the amphitheatre formed part of Augusta Emerita, one of the most important Roman cities in Hispania. Built around 8 BC during the reign of Emperor Augustus, the structure stood beside the city's theatre and became a centerpiece of Roman public life. Archaeological excavations beginning in the early 20th century gradually uncovered the arena, seating sections, underground facilities, and engineering systems that transformed what appeared to be a simple entertainment venue into one of the most sophisticated public structures of the ancient world. The more researchers study the amphitheatre, the more difficult a question becomes to answer. How did Roman engineers create a building capable of accommodating approximately 15,000 spectators without steel reinforcement, powered machinery, computers, or modern engineering mathematics? The first mystery involves structural design. The amphitheatre measures roughly 126 metres long and 102 metres wide. While these dimensions are smaller than the Colosseum in Rome, they remain enormous for a structure built more than 2 millennia ago. Modern engineers rely on advanced software capable of calculating stress distributions across millions of structural elements, yet Roman builders possessed none of these tools. Even so, the amphitheatre survives. Its weight is distributed through a network of arches, vaults, retaining walls, and radial support corridors. The arrangement appears deceptively simple, but structural analysis shows that the design efficiently channels loads through the building in ways remarkably similar to principles used in modern stadium engineering. Researchers can calculate how the forces move through the structure today, but what remains unclear is how Roman engineers calculated these forces before modern mathematics existed. No surviving Roman document explains the exact design methodology used to determine wall thicknesses, arch dimensions, or load distribution. Some knowledge likely came from centuries of accumulated experience, but experience alone may not fully explain the consistency achieved across hundreds of Roman public buildings throughout the empire. The second mystery concerns the speed of crowd movement. Today, crowd management represents one of the most important aspects of stadium design. Engineers use computer simulations to predict how thousands of people will enter and leave large venues, and poor design can create bottlenecks that become deadly during emergencies. The amphitheatre of Mérida appears to have solved this problem more than 2,000 years ago. The seating areas are connected through a carefully organised system of corridors, stairways, and access points. Spectators could reach assigned seating sections without crossing major traffic flows, while multiple entrances distributed movement throughout the structure. The entire design minimized congestion while maximizing visibility. Studies of modern stadium evacuation systems have revealed principles remarkably similar to those employed by Roman architects. The question is how they developed this understanding. Did Roman engineers conduct practical experiments? Did they possess mathematical models that have been lost? Or was this knowledge refined through generations of observation and construction? Experience? No definitive answer exists. The third mystery lies beneath the arena floor. Archaeologists have identified underground chambers, corridors, and service areas beneath the amphitheatre. These spaces housed animals, gladiators, equipment, and personnel before events began. The arrangement reveals a surprisingly sophisticated logistical system. Large public spectacles required careful coordination. Animals had to remain separated from spectators. Gladiators needed controlled access to the arena, and equipment had to be stored and transported efficiently. The underground complex functioned almost like a backstage operating system, hidden beneath the visible structure. At the Colosseum in Rome, excavations revealed an elaborate hypogeum containing elevators, trapdoors, and lifting mechanisms powered by human labour. More than 60 animal lifts may have existed there. While Merida's underground remains are less completely preserved, archaeologists continue to debate whether similar mechanical systems once operated beneath the arena. If they did, Roman engineers may have created complex lifting technology capable of moving large loads vertically using only ropes, pulleys, counterweights, and manpower. Many details remain unknown. The fourth mystery involves acoustics. An open-air amphitheatre should theoretically create significant challenges for sound transmission. Without electronic amplification, voices and announcements would struggle to reach thousands of spectators. Yet acoustic studies conducted in Roman entertainment structures repeatedly demonstrate surprisingly effective sound propagation. The geometry of the seating areas, the slope of the cavea, and the reflective properties of stone surfaces appear to work together to amplify and distribute sound. Modern acoustic engineers often rely on computer modelling to optimize performance, but Roman builders achieved practical solutions without microphones, speakers, or digital simulations. Whether this knowledge resulted from formal acoustic understanding or generations of empirical experimentation remains uncertain. The fifth mystery concerns construction logistics. The amphitheatre required enormous quantities of stone, brick, mortar, and labour. Historians estimate that major Roman construction projects often involved thousands of workers operating simultaneously. Transporting stone alone represented a significant challenge. Some individual blocks weighed several tons. Modern construction sites depend on hydraulic cranes, trucks, and heavy machinery, whereas Roman builders relied primarily on animals, wooden cranes, ropes, and human labour. Experimental archaeology has demonstrated that Roman treadwheel cranes could lift loads exceeding several tons. Some reconstructions suggest lifting capacities comparable to small modern construction cranes. Yet many practical aspects of large-scale Roman building operations remain poorly understood. How were schedules coordinated? How were materials delivered precisely when needed? How were thousands of labourers organised efficiently across massive construction sites? The archaeological evidence reveals the results, but not always the process. The sixth mystery involves Roman concrete and durability. Although much of the amphitheatre of Merida consists of stone masonry, Roman construction frequently incorporated concrete technology that continues to attract scientific attention today. Modern laboratory analysis has shown that Roman concrete often contained volcanic ash, lime, and aggregate materials that created unusual chemical reactions. In some cases, microscopic mineral formations appear capable of helping repair cracks over time. Researchers comparing Roman marine concrete with certain modern formulations have found examples where ancient materials exhibit superior, long-term durability. Some Roman harbour structures have survived nearly 2,000 years of wave action. While Merida does not sit beside the sea, it forms part of a broader engineering tradition whose material science remains only partially understood. Scientists can identify ingredients, but reconstructing the complete manufacturing knowledge is more difficult. The seventh mystery concerns surveying and precision. The amphitheatre was not constructed in isolation. It formed part of a carefully planned urban landscape connected to roads, water systems, public buildings, and administrative infrastructure. Roman surveyors lacked lasers, satellites, GPS, and electronic measuring equipment. Nevertheless, measurements taken across Roman cities often reveal astonishing consistency. The alignment of major public structures, transportation routes, and civic spaces demonstrates a degree of precision that required highly developed surveying techniques. Roman instruments such as the groma and chorobates survive in historical descriptions, but many practical details regarding their use remain uncertain. Some researchers argue that Roman surveying represented one of the greatest technological achievements of the ancient world. The lost city of Tiwanaku is hidden deep in the Sierra Nevada de Santa Marta in northern Colombia, a mountain range that rises from the Caribbean coast to more than 5,700 meters in less than 50 kilometers. Long before Europeans arrived in South America, the Tairona civilization built a network of settlements across these mountains. At the center was Tiwanaku, better known today as Ciudad Perdida, or the Lost City. What makes the site remarkable is not only its age or isolation. The greatest mystery is how a society without iron tools, wheeled transportation, or large draft animals managed to build a city that could withstand one of the harshest tropical environments on Earth for more than 1,000 years. The modern discovery of the city occurred in the 1970s when local treasure hunters, known as huasaqueros, followed ancient stone stairways into jungle-covered mountains. Their discoveries attracted the attention of Colombian archaeologists, who soon realized that the site represented one of the largest pre-Columbian urban centers ever found in South America. Archaeological investigations revealed more than 250 stone terraces connected by roads, staircases, retaining walls, and drainage systems spread across steep mountain slopes. Radiocarbon dating indicates that the city was established around AD 800, making it several centuries older than Machu Picchu in Peru. The first great mystery concerns the engineering of the mountains themselves. Modern engineers understand how difficult it is to construct stable settlements on steep slopes. Landslides, erosion, and heavy rainfall constantly threaten infrastructure. Yet the Tairona transformed mountainsides into a complex urban landscape through the construction of hundreds of artificial terraces. Some terraces required moving thousands of cubic meters of earth and stone. Unlike the Inca, who often built on relatively stable highland plateaus, the Tairona worked within dense tropical mountains where annual rainfall frequently exceeds 4,000 millimeters. The question is simple: how did they know where to build? Modern geotechnical engineers use soil analysis, slope stability calculations, and hydrological models before beginning construction. The Tairona possessed none of these technologies. Nevertheless, many terraces remain remarkably stable after more than 1,200 years. Archaeologists have found evidence that builders carefully selected locations where natural bedrock provided support while retaining walls distributed pressure across the slope. The precision suggests a sophisticated understanding of mountain geology acquired entirely through observation and experience. Yet the methods used to identify safe construction zones remain unknown. The second mystery involves the city's extraordinary drainage system. Tropical rainfall destroys ancient settlements throughout the world. In regions such as Southeast Asia, abandoned cities often disappear beneath vegetation within centuries. Tiwanaku should have suffered the same fate. Instead, much of its infrastructure survived. Excavations revealed an extensive network of stone-lined channels running beneath terraces, plazas, and pathways. These channels directed rainwater away from critical structures and prevented erosion. Engineers studying the system have noted that many channels still function today. Water continues to flow through routes established more than a millennium ago. The scale of this achievement becomes apparent when compared to other ancient civilizations. The Romans constructed famous aqueducts across Europe. The Maya developed sophisticated reservoirs in Central America. The Inca built mountain drainage systems at Machu Picchu. Yet Tiwanaku accomplished comparable hydrological control in one of the wettest environments inhabited by any major pre-Columbian civilization. What remains unexplained is how the system was designed. There are no surviving plans, measurements, or written instructions. The Tairona left no deciphered writing system. Everything depended upon practical knowledge transmitted across generations. Modern archaeology can map the channels, but it cannot fully reconstruct the intellectual framework behind their design. The third mystery concerns transportation. Every stone used in the city had to be moved through rugged terrain covered by dense forest. The Tairona lacked horses, oxen, and wheeled vehicles. South America possessed no equivalent of the draft animals used in ancient Europe or Asia. Yet thousands of tons of stone were transported and positioned with remarkable accuracy. Some terraces contain retaining walls several meters high. Building such structures required coordinated labor, careful planning, and methods for moving heavy materials uphill. Experimental archaeology suggests that teams using ropes, wooden sleds, and human labor could have accomplished the task. However, calculations indicate that moving even a single large stone block up steep mountain slopes would require significant manpower. So this raises a larger question. If constructing one terrace required such effort, how did the Tairona build hundreds? The city appears to represent generations of continuous engineering investment. Archaeologists estimate that the broader Tairona network may have supported tens of thousands of people. Such projects imply organizational capabilities far beyond what earlier researchers imagined for tropical chiefdoms. The fourth mystery is the city's hidden road network. Surveys have revealed stone-paved pathways connecting settlements throughout the Sierra Nevada. Some routes cross steep ridges, descend into river valleys, and climb mountains again. Together they formed a transportation system linking communities separated by difficult terrain. The engineering challenge is comparable to aspects of the Inca road system, which eventually stretched more than 40 kilometers across western South America. While the Tairona network was smaller, it faced unique environmental obstacles. Tropical vegetation grows rapidly. Heavy rainfall erodes exposed surfaces. Rivers frequently change course. Yet many ancient pathways remained usable centuries after abandonment. Researchers continue to debate how these routes were maintained. Did specialized workers inspect and repair roads? Was labor organized through local communities? Or did political authorities coordinate construction across multiple settlements? The archaeological evidence provides clues, but no definitive answers. The fifth mystery involves urban planning. At first glance, Tairona appears chaotic because it follows the contours of the mountains. However, detailed surveys reveal underlying patterns. Residential areas, ceremonial spaces, administrative centers, and agricultural zones appear carefully organized. Certain terraces occupy strategic positions overlooking transportation corridors. Others are linked to plazas that may have served social or political functions. The city was not randomly assembled, it was planned. This presents a paradox. Many ancient civilizations relied on writing, bureaucracy, and centralized records to coordinate large construction projects. The Tairona appear to have achieved comparable levels of organization without surviving evidence of such systems. The knowledge required to manage labor, resources, and engineering projects remains largely invisible. The sixth mystery concerns agriculture. Supporting a large mountain population required intensive food production. Archaeologists have identified extensive agricultural terraces throughout the Sierra Nevada region. These systems reduced erosion, conserved water, and expanded cultivable land. What remains unclear is how agricultural productivity was maintained over centuries. Tropical soils often lose nutrients rapidly. Modern farmers frequently depend on fertilizers and scientific soil management. The Tairona achieved long-term sustainability using methods that remain poorly understood. Studies of soil chemistry suggest that indigenous farmers may have employed sophisticated land management strategies involving crop diversity, organic enrichment, and landscape engineering. However, direct evidence is limited. Much of the agricultural system vanished long before modern researchers arrived. The seventh mystery is how the Tairona coordinated hundreds of mountain settlements. Despite the difficult terrain, artifacts from different sites show strikingly similar craftsmanship and design, suggesting strong communication networks that spread technical knowledge. Without written records, archaeologists can only speculate. Some believe ritual specialists carried knowledge between communities, while others point to elite family networks built through marriage and trade. Whatever the method, it helped preserve engineering traditions for centuries. The final mystery is the disappearance of the city itself. Spanish chroniclers recorded encounters with Tairona communities during the 16th century. European diseases, warfare, forced resettlement, and colonial disruption devastated indigenous populations throughout the region. By the time the city was abandoned, much of the knowledge responsible for its construction had already begun to disappear. The tragedy is that the physical structures survived, while the engineering knowledge behind them did not. What do you think was the true secret behind Taranaka's survival for more than 1,000 years? Superior environmental engineering, a lost system of knowledge, or something archaeologists have not yet discovered? During excavations for the city's metro system, beginning in the early 21st century, archaeologists uncovered an extraordinary underground landscape of Roman and Byzantine streets, marketplaces, water systems, workshops, and monumental structures. What emerged was not simply a collection of ruins. It was an entire ancient city preserved beneath a living modern metropolis. The discoveries revealed engineering achievements that continue to raise difficult questions. How did ancient builders construct infrastructure capable of surviving earthquakes, invasions, fires, and nearly 2,000 years of urban development? More importantly, how did they achieve such remarkable technical precision without the instruments, materials, and scientific theories available today? One of the greatest mysteries involves the buried city itself. Archaeologists working beneath modern Thessaloniki discovered layers of construction stacked one above another, representing centuries of continuous occupation. Unlike sites abandoned and preserved in isolation, Thessaloniki remained inhabited throughout Roman, Byzantine, Ottoman, and modern periods. Each generation built upon the remains of earlier structures. The result is an archaeological sequence resembling a giant vertical archive of urban engineering. In some areas, multiple building phases are compressed within only a few meters of depth. Maintaining structural stability under such conditions presents challenges even for modern engineers. Yet ancient builders repeatedly expanded, renovated, and reconstructed major districts while keeping the city functional. How they managed foundations across centuries of changing urban landscapes remains only partially understood. The second mystery centers on the city's remarkable resistance to earthquakes. Thessaloniki sits within one of the most seismically active regions of the eastern Mediterranean. Historical records document numerous destructive earthquakes affecting northern Greece. Nevertheless, several Roman and Byzantine structures survived for centuries. The most famous example is the Rotunda, originally constructed during the reign of Emperor Galerius around AD 306. Its massive dome remains standing after more than 17 centuries. Modern engineers studying the structure have identified sophisticated methods of load distribution throughout the building. Thick masonry walls, carefully calculated geometry, and strategic use of brick layers appear to have helped absorb seismic forces. Yet there is no evidence that Roman architects possessed anything resembling modern structural engineering equations. The mystery is not that the rotunda survives. The mystery is that builders without advanced mathematics created a structure capable of enduring repeated earthquakes while many much newer buildings failed. The third mystery concerns the construction of the rotunda itself. The building measures approximately 24.5 meters in internal diameter and rises nearly 30 meters high. This places it among the largest surviving masonry domes from the ancient world. Comparisons are often made with the Pantheon in Rome, whose famous dome spans approximately 43 meters. While smaller than the Pantheon, the rotunda presents a different puzzle. Unlike many monumental Roman buildings that benefited from centuries of architectural development, the rotunda was constructed in a provincial city far from the empire's capital. Transporting the enormous quantities of stone, brick, mortar, and timber required for such a project would have represented a massive logistical challenge. Researchers estimate that thousands of tons of material were needed. Yet no detailed records survive explaining how construction was organized, how lifting systems operated, or how engineers coordinated such a complex project. The building stands as evidence of capabilities that exceed what many historians once believed possible for provincial Roman construction. Another mystery involves Roman concrete and mortar technologies used throughout Thessaloniki. Modern laboratory analyses reveal that many ancient mortars possess extraordinary durability. Some contain volcanic materials imported from distant regions, while others exhibit mineral reactions that continue strengthening the material long after construction. Recent scientific studies of Roman concrete elsewhere in the Mediterranean have shown evidence of self-healing clay mechanisms capable of sealing microscopic cracks through chemical processes. Similar characteristics have been observed in some materials recovered from Thessaloniki. The challenge is understanding how ancient builders developed these formulas. Modern concrete production relies upon chemistry, materials science, and industrial quality control. Roman engineers possessed none of these disciplines in a modern sense, yet their structures routinely outlast concrete produced only a century ago. Whether this reflects lost empirical knowledge or deeper understanding remains debated. The fifth mystery concerns the city's underground water management systems. Excavations have uncovered extensive drainage networks beneath ancient streets. These systems collected rainwater, removed wastewater, and protected urban districts from flooding. Designing such infrastructure requires careful calculations of gradient. Even a small error can prevent water from flowing efficiently. Surveys conducted on surviving sections indicate surprisingly precise alignment over considerable distances. Some channels maintain consistent slopes despite crossing uneven terrain. The accuracy achieved rivals that of drainage systems designed using far more advanced tools. Archaeologists know that Roman surveyors employed instruments such as the chorobates and groma, but questions remain regarding the practical precision achievable with these devices. The engineering evidence suggests a level of surveying expertise that is still difficult to fully reconstruct. The sixth mystery emerged during metro excavations beneath the modern city centre. Archaeologists uncovered a remarkably preserved section of the ancient main avenue known as the Decumanus Maximus. The road included paved surfaces, drainage channels, commercial buildings, workshops, and public spaces. Some researchers described the discovery as a buried urban landscape, comparable in significance to sections of Pompeii. What makes the avenue remarkable is not merely its preservation but its organisation. The street functioned as part of an integrated urban system connecting transportation, commerce, water management, and public administration. Modern cities often require separate engineering teams to coordinate such infrastructure. Ancient planners achieved similar integration nearly 2 millennia ago. How administrative authorities coordinated projects on scale remains poorly understood because much of the documentary evidence has disappeared. Another technological mystery involves long-distance material transportation. Thessaloniki became one of the most important cities in the Roman and Byzantine worlds. Large public buildings required immense quantities of construction materials. Marble, stone, timber, and specialized decorative elements arrived from various regions of the Mediterranean. Some marble varieties identified in surviving monuments originated hundreds of kilometers away. Moving such cargo required sophisticated supply chains involving quarries, ports, ships, roads, and labor forces. Historians can estimate trade routes, but reconstructing the exact logistical mechanisms remains difficult. The scale of construction suggests organizational capabilities comparable to those used for major imperial projects elsewhere in the Roman Empire. The eighth mystery concerns lost workshops and manufacturing districts hidden beneath the modern city. Excavations have revealed evidence of metalworking, ceramics production, glass manufacturing, and other industries. Chemical analyses of artifacts indicate consistent production standards. In some cases, products exhibit remarkable uniformity despite being created long before industrial manufacturing. Achieving such consistency requires knowledge of temperature control, raw material selection, and production techniques. Yet the furnaces, tools, and operational methods responsible for many of these products remain only partially preserved. Archaeologists often possess the finished artifacts but lack complete evidence for the technologies that produced them. Perhaps the greatest mystery of Thessaloniki is how much remains hidden. Modern excavations have uncovered only a small part of the ancient city, while large areas still lie beneath roads, buildings, and infrastructure. Surveys suggest that buried streets, water systems, workshops, and public buildings may still survive underground. Unlike many archaeological sites, Thessaloniki was never abandoned. It is a city that never disappeared. Villa of Augustus is a Roman imperial villa buried beneath the modern town of Somma Vesuviana on the northern slopes of Mount Vesuvius in southern Italy. Hidden beneath volcanic deposits for nearly 2,000 years, the site presents one of the most intriguing technological mysteries of the Roman world. Archaeologists can identify the walls, measure the rooms, and reconstruct portions of the building, yet many of the engineering techniques that allowed the complex to survive repeated volcanic disasters remain only partially understood. The greatest mystery is not who lived there, but how Roman engineers created a structure capable of enduring conditions that would destroy many modern buildings. The villa was discovered during archaeological investigations that began in the early 2000s beneath several meters of volcanic deposits. Excavations revealed an enormous elite complex covering thousands of square meters. The discovery attracted international attention because some researchers proposed that the structure may be connected to Emperor Augustus, who died in AD 14. Whether or not Augustus himself occupied the villa, the scale of the architecture clearly indicates an imperial-level residence. Buried beneath layers of ash, mud, and volcanic debris, the complex preserved evidence of engineering knowledge that still raises questions today. The first mystery concerns survival. Mount Vesuvius is one of the most dangerous volcanoes in Europe. The famous eruption of AD 79 destroyed Pompeii and Herculaneum, but later eruptions continued to reshape the surrounding landscape for centuries. The villa at Somma Vesuviana endured multiple volcanic events, including the massive eruption of AD 472. Geological studies indicate that several meters of volcanic material accumulated above parts of the structure. Modern engineers know that volcanic deposits can exert tremendous pressure on walls and roofs. Wet ash becomes even heavier, often reaching densities exceeding 1,000 kilograms per cubic meter. Under such loads, many buildings collapse, yet significant portions of the villa remain standing. Archaeologists have documented walls exceeding 1 meter in thickness, carefully bonded with Roman concrete and stone masonry. The remarkable preservation raises an important question. Did Roman builders intentionally design the structure to withstand extreme environmental stress, or was its survival simply the result of over-engineering? Modern structural analysis suggests that the distribution of weight through arches, vaults, and thick load-bearing walls played a critical role. However, researchers still debate how Roman architects determined these proportions without modern mathematics, computer simulations, or structural engineering software. The second mystery involves Roman concrete. Samples recovered from the villa demonstrate the use of the famous Roman construction material known as opus caementicium. This concrete incorporated volcanic ash from the Campanian region, lime, and aggregate. Modern laboratory analysis has revealed something extraordinary. Unlike ordinary Portland cement, which often deteriorates within decades under harsh conditions, Roman concrete can continue strengthening over time through chemical interactions between volcanic minerals and groundwater. Studies comparing ancient Roman concrete with modern equivalents have found that certain mineral crystals develop inside microscopic fractures. These crystals can partially seal cracks before they expand into major structural failures. Some Roman harbour structures have survived almost 2,000 years of exposure to seawater. The villa appears to preserve evidence of the same technological tradition. The mystery is whether Roman builders understood the chemistry behind these materials, or whether centuries of experimentation accidentally produced one of history's most durable construction technologies. To appreciate the scale of this achievement, consider a comparison. Many reinforced concrete structures built during the 20th century require major repairs after 50 to 100 years. The villa's masonry has endured earthquakes, volcanic eruptions, weathering, and nearly 2 millennia of burial. Even with modern materials science, researchers are still studying Roman concrete in hopes of developing longer-lasting sustainable construction methods. The third mystery concerns water management. Excavations revealed sophisticated hydraulic features, including channels, storage systems, drainage networks, and water control installations. Roman engineers understood that water was both essential and destructive. A poorly designed drainage system could undermine foundations, flood storage areas, and destabilize walls. The villa's hydraulic network appears carefully integrated into the architecture itself. The challenge becomes even more remarkable when considering the local environment. The slopes of Vesuvius experience intense rainfall, rapid runoff, and periodic geological instability. Yet the villa operated successfully for decades, perhaps centuries. Modern survey equipment allows engineers to calculate gradients with millimeter precision. Roman builders relied on simple instruments such as the chorobates and groma. How they consistently achieved the necessary accuracy across large construction projects remains a subject of fascination. The fourth mystery is the heating system. Evidence suggests that parts of the villa employed hypocaust technology, one of the most advanced climate control systems of the ancient world. In a hypocaust, furnaces generated hot air that circulated beneath raised floors and through hollow wall spaces. The result was a form of central heating more than 500 years before similar systems became common in Europe. Creating an efficient hypocaust required sophisticated understanding of airflow, heat transfer, fuel consumption, and architectural planning. Rooms needed carefully positioned vents. Floors had to be elevated on hundreds of small pillars. Temperatures had to remain comfortable without damaging structural materials. Modern engineers can model these systems using computational fluid dynamics. Roman engineers achieved functional results using practical experience alone. Exactly how this knowledge was standardized and transmitted across generations remains unclear. The fifth mystery involves logistics. The villa was not a simple country house. Archaeologists uncovered monumental spaces, storage facilities, decorative architecture, and evidence of large-scale economic activity. Constructing such a complex required enormous quantities of stone, timber, brick, tiles, and concrete. Tens of thousands of individual building components had to be produced, transported, and assembled. Historians estimate that large Roman construction projects sometimes involved hundreds or even thousands of workers. Materials moved through supply networks extending across the Bay of Naples. Yet surprisingly little documentation survives explaining how these operations were coordinated. Without cranes powered by electricity, diesel trucks, or modern project management systems, Roman builders repeatedly completed structures of extraordinary complexity. The villa highlights how much organizational knowledge has disappeared from the historical record. The sixth mystery concerns earthquake resistance. Southern Italy lies within an active tectonic region. Earthquakes affected Campania throughout Roman history. Modern structural engineering employs steel reinforcement, seismic dampers, and computer-designed foundations to reduce earthquake damage. Roman buildings lacked such technologies, yet many survived centuries of seismic activity. Researchers studying Roman architecture have identified features that may have improved resilience. Thick walls, flexible mortar joints, strategic use of arches, and distributed structural loads all appear to reduce stress concentrations. However, There remains no complete explanation for why some Roman structures survived repeated earthquakes while others collapsed. The villa may preserve valuable clues regarding ancient approaches to seismic engineering. The discovery of Angkor Thom lies near modern Siem Reap, Cambodia, at the heart of the ancient Khmer Empire. Although European explorers documented the ruins during the 19th century, the true scale of the city remained unknown for more than a century. Everything changed in the early 21st century when archaeologists began using airborne LiDAR technology. By firing millions of laser pulses through the jungle canopy, researchers revealed an enormous urban landscape hidden beneath the forest. What appeared to be a collection of temples turned out to be part of one of the largest pre-industrial cities ever built. Surveys conducted by the Greater Angkor Project revealed an urban complex covering more than 1,000 square kilometers, transforming Angkor from a famous archaeological site into one of the most important engineering mysteries on Earth. The first mystery is the hydraulic system itself. Angkor Thom was not simply a walled city, but the center of an immense network of reservoirs, canals, embankments, spillways, and artificial waterways designed to control seasonal monsoon floods. The scale of this system is astonishing. The nearby West Baray Reservoir measures approximately 8 kilometers long and more than 2 kilometers wide, containing an estimated 50 million cubic meters of water. To put that into perspective, the reservoir holds enough water to fill roughly 20 Olympic swimming pools. Across the Angkor region, multiple reservoirs and canals work together to store, transport, and redistribute water throughout the year. Modern hydrologists studying the system have discovered evidence of remarkable sophistication, showing that water could be redirected through interconnected channels depending on seasonal conditions. During heavy monsoon rains, excess water could be diverted away from critical infrastructure, while during dry periods, stored water could support agriculture. Yet the greatest question remains unanswered. How did Khmer engineers design and maintain such a vast hydraulic network without modern surveying, equipment, advanced mathematics, or industrial construction technology? Even today, managing water across 1,000 square kilometer landscape requires complex engineering models, yet the Khmer accomplished it more than 800 years ago. The second mystery involves precision city planning. Angkor Thom was established during the reign of King Jayavarman VII in the late 12th century and forms an enormous square approximately 3 kilometers on each side. Massive walls surround the city, while a moat nearly 100 meters wide encircles the entire perimeter. The gates align closely with the cardinal directions. Such precision might appear ordinary on a modern map, but constructing a nearly perfect geometric city within a tropical environment presented extraordinary challenges. Surveyors today use GPS receivers capable of centimeter-level accuracy, yet medieval Khmer engineers possessed no such tools. Nevertheless, they created a city whose overall alignment rivals that of many famous ancient capitals. Similar achievements are often discussed in relation to places such as the Egyptian pyramids or Roman military camps, and Angkor Thom belongs in the same conversation. Archaeologists still debate the exact techniques used to establish these alignments across such a large area. The third mystery concerns the construction of Bayon Temple, the spiritual center of Angkor Thom. Bayon contains more than 50 towers decorated with over 200 enormous stone faces. Each face rises several meters high and was carved with extraordinary symmetry. Some scholars believe the faces represent Avalokiteshvara, the Buddhist bodhisattva of compassion, while others suggest they may portray Jayavarman VII himself. The engineering challenge is extraordinary because many of these faces sit dozens of meters above ground level, yet their proportions remain remarkably consistent, despite being positioned on complex tower structures. Researchers continue to debate whether the faces were carved before the blocks were lifted into position or after construction was completed. If they were carved on the ground, engineers had to achieve near-perfect placement during assembly. If they were carved in place, workers would have needed elaborate scaffolding systems and highly precise measuring techniques. No written records survive to explain how this process was carried out. The fourth mystery involves transportation. Most of the sandstone used in Angkor Thom originated from quarries in the Kulin Hills, approximately 30 to 40 kilometers away. Millions of stone blocks were transported across rivers, canals, and difficult terrain, with some blocks weighing several tons. Modern estimates suggest that tens of millions of tons of stone were moved throughout the Angkor region over centuries of construction. Comparisons help illustrate the scale of this achievement. The Great Pyramid of Giza contains roughly 2.3 million stone blocks, yet Angkor's total building program extended across a much larger urban landscape and required the continuous movement of construction materials over long distances. Archaeologists have identified ancient canals linking quarry areas to the city, suggesting that water transport played a major role. However, the complete logistics system remains poorly understood. Questions remain regarding how many workers were involved, how long transportation took, and how massive stones were loaded and unloaded without cranes. The available evidence remains incomplete. The fifth mystery is hidden beneath the ground. Angkor Thom was constructed in a region heavily affected by seasonal flooding and unstable soils. Despite these conditions, many structures have survived for more than 8 centuries. Engineers appear to have understood drainage, soil stabilization, and load distribution at a sophisticated level. Modern geotechnical studies reveal carefully prepared foundations beneath major monuments, while water management features often worked together with structural engineering solutions. In some locations, canals and reservoirs may have helped regulate groundwater levels. This raises an important question. Did Khmer engineers possess practical knowledge of soil mechanics centuries before the scientific principles were formally understood? The surviving structures suggest that they may have. The sixth mystery concerns population support. Angkor has often been compared with the largest cities of the medieval world. Some estimates suggest that the Greater Angkor region may have supported between 700,000 and 1 million inhabitants at its peak. If accurate, this would place Angkor among the most populous urban centres on Earth during the 12th and 13th centuries. Supporting such a population required enormous agricultural productivity. Rice cultivation depended on reliable water control, while food distribution required extensive infrastructure. Labor organization had to coordinate construction, maintenance, transportation, and administration. Yet the Khmer left surprisingly few records explaining how this gigantic urban machine functioned. The physical evidence demonstrates success, but the organizational mechanisms behind that success remain largely invisible. The seventh mystery is the collapse of the system. By the 15th century, Angkor's political importance had declined dramatically. Researchers investigating sediment cores, tree rings, and climate records discovered evidence of severe environmental instability. Southeast Asia experienced prolonged droughts interrupted by episodes of unusually intense rainfall, and these extreme climate events may have placed enormous stress on the hydraulic network. Computer simulations suggest that parts of the water management system became increasingly vulnerable over time. Channels eroded, reservoirs accumulated sediment, and infrastructure required constant maintenance. Some scholars believe Angkor became a victim of its own complexity. As the larger the system grew, the harder it became to manage. Yet, no single explanation fully accounts for the decline. Climate change, political conflict, shifting trade routes, and institutional challenges may all have contributed, and the exact sequence of events remains uncertain. Hala Sultan Tekke, on the southern coast of Cyprus near modern Larnaca, was one of the wealthiest cities in the ancient Mediterranean. More than 200 years ago, Ships arrived here from Egypt, Greece, Anatolia, the Levant, and possibly lands far beyond. Yet many of the technologies that made this vast trading network possible remain unexplained. The site was first identified through archaeological investigations during the 20th century, but major discoveries accelerated after extensive excavations led by researchers from the University of Gothenburg, beginning in the 1970s and continuing into the 21st century. What emerged from the ground was not a small coastal settlement, but a major Bronze Age city covering as much as 25 to 50 hectares, making it one of the largest urban centres known in Cyprus during the Late Bronze Age. The discoveries immediately raised a question: how did a city on an island become one of the most important commercial hubs in the entire Eastern Mediterranean around 1500 to 1150 BC? Archaeologists have uncovered evidence of an astonishing international economy. Imported pottery from Mycenae in Greece, ivory from Africa, precious stones originating in Central Asia, Egyptian artifacts, and luxury goods from the Levant have all been found at the site. Chemical analyses indicate that goods travelled thousands of kilometres before reaching Hala Sultan Tekke, and some materials may have crossed distances exceeding 3,000 kilometres. For comparison, the distance between Cyprus and Egypt is roughly 500 kilometres, while the distance between Cyprus and mainland Greece exceeds 800 kilometres. Yet trade connections linked all of these regions into a single economic system. The mystery is not that trade existed, but the scale on which it operated. Without modern navigation equipment, advanced maps, or centralized communications, merchants somehow coordinated an international trading network comparable in complexity to some later Iron Age economies. Researchers still debate how information moved efficiently enough to sustain such extensive commercial activity. Cyprus was the primary source of copper for much of the Eastern Mediterranean during the Bronze Age. In fact, many historians believe the name Cyprus itself became closely associated with copper production. Large oxide-shaped copper ingots recovered from shipwrecks, such as the famous Uluburun shipwreck, demonstrate the enormous scale of Bronze Age metal trade, with some ingots weighing around 25 kilograms each. Thousands of such ingots circulated across Mediterranean trade routes. Producing this volume of copper required mining, transportation, smelting, quality control, and distribution systems operating with remarkable efficiency. Yet archaeologists still struggle to reconstruct the complete industrial infrastructure behind this production. Questions remain about how temperatures exceeding 100 degrees Celsius were maintained consistently in Bronze Age furnaces, how ore quality was standardized, and how production was organized without modern industrial management. The archaeological evidence suggests a sophisticated metallurgical economy, but many of the technical details remain unknown. A city engaged in international commerce should leave behind extensive administrative records. Ancient Egypt produced written archives. The Hittites produced thousands of clay tablets, and Mesopotamian cities generated entire libraries of economic records. Hala Sultan Tekke, however, presents a puzzle. The city clearly managed warehouses, imported luxury goods, industrial production, and maritime trade, yet very little evidence survives explaining how these activities were coordinated. Who controlled trade agreements? Who organized shipping schedules? Who tracked incoming and outgoing cargo? The economic system appears highly sophisticated, but much of its administrative structure remains invisible. Excavations reveal carefully organized residential districts, workshops, storage facilities, and industrial zones. This was not random growth. City appears planned. Road systems connected different sectors, specialized production areas were separated from living spaces, and large storage facilities indicate centralized management of valuable goods. Researchers estimate that several thousand people may have lived here during its peak. Compared with many contemporary settlements across Europe, Hala Sultan Tekke exhibited a level of urban organization more comparable to major cities of the Near East. How such planning knowledge developed and spread across the Bronze Age Mediterranean remains uncertain. Every major city depends on water, and this simple fact creates another mystery. Southern Cyprus experiences long dry seasons, meaning that sustaining a large population, industrial production, livestock, and visiting merchants required dependable water supplies. Yet the complete hydraulic system remains poorly understood. Some scholars suggest wells and groundwater sources played a major role, while others believe water collection and storage systems were more sophisticated than currently recognized. The city survived for centuries, indicating that its inhabitants solved a difficult environmental challenge, but exactly how they achieved this remains debated. This may be the greatest mystery of all. Nothing about Hala Sultan makes sense unless its inhabitants mastered the sea. The city's wealth depended on ships, its copper exports depended on ships, its imported luxury goods depended on ships, and ultimately its survival depended on ships. Yet almost none of those ships survive. Wood decays, ropes disappear, sails vanish, and the technology that connected entire civilizations has largely been erased by time. Archaeologists can estimate trade routes, but reconstructing the ships themselves is far more difficult. The Uluburun shipwreck, discovered off the coast of Turkey and dating to around 1300 BC, offers one of the few surviving glimpses into Bronze Age maritime technology. The vessel carried more than 10 tons of cargo, including copper ingots, tin ingots, glass, ivory, jewelry, and luxury goods. Its existence demonstrates that late Bronze Age ships could transport enormous loads across open water. But this raises a larger question. How did sailors navigate? The Gamadi compass would not appear for centuries. Accurate nautical charts did not exist, and there were no lighthouses across the Mediterranean guiding vessels from port to port. Yet ships repeatedly crossed hundreds or even thousands of kilometers. Some researchers believe sailors navigated using stars, prevailing winds, seasonal weather patterns, ocean swells, and detailed mental maps passed down through generations. Others argue that Bronze Age mariners possessed levels of practical astronomical knowledge that modern historians still underestimate. Another mystery concerns ship construction itself. Bronze Age shipbuilders created vessels capable of carrying cargo weighing many tons while surviving storms, waves, and long-distance voyages. The engineering challenge was immense. A vessel carrying 10 tons of copper could easily sink if weight distribution was poorly managed. Hull strength, buoyancy, sail design, and cargo arrangement all required sophisticated knowledge. Unlike monumental architecture, which survives for millennia, shipbuilding technology leaves very little evidence behind. As a result, one of humanity's most important technological achievements may also be one of its least understood. Without these ships, Hala Sultan could never have become a major international port. Yet the methods that made such maritime success possible remain largely hidden beneath the sea. Around 1200 BC, the Bronze Age world experienced one of history's greatest collapses. Major powers declined, trade routes fragmented, cities were destroyed, and entire kingdoms disappeared. Hala Sultan was caught in this crisis. Evidence suggests the city was eventually abandoned as the wider Eastern Mediterranean trading system unraveled. The causes remain controversial. Earthquakes, drought, warfare, political instability, economic collapse, and the movements of the mysterious sea peoples have all been proposed. No single explanation fully accounts for the evidence. The city that once connected continents simply faded from history. If the shipbuilders of Hala Sultan could cross the Mediterranean without modern technology, what other ancient engineering secrets have been lost forever? Agios Athanasios is a Macedonian tomb complex near Thessaloniki, northern Greece, where paintings more than 300 years old still retain remarkable detail and colour. The site raises a question that archaeologists have not fully answered. How did ancient craftsmen create artworks capable of surviving for over 2 millennia, while preserving visual qualities that rival much younger masterpieces? The tomb was discovered in 1994 during construction work near the modern village of Agios Athanasios, approximately 15 kilometers west of Thessaloniki. Archaeologists soon realized they had uncovered one of the best preserved Macedonian tombs ever found. Dating to the late 4th century BC, shortly after the death of Alexander the Great in 323 BC, the monument belonged to an elite member of the Macedonian aristocracy. What initially appeared to be another burial chamber quickly became one of the most important discoveries for understanding ancient technology, engineering, and artistic knowledge in the Hellenistic world. The greatest mystery of Agios Athanasios is not the tomb itself, but the paintings covering its walls. More than 23 centuries after they were created, many figures remain visible with extraordinary clarity. Warriors, banquet participants, garments, weapons, and decorative motifs can still be distinguished in remarkable detail. This preservation is extraordinary when compared with many ancient paintings elsewhere. Most Greek panel paintings have completely disappeared, and even numerous Roman wall paintings suffered extensive fading, despite being hundreds of years younger. Yet at Agios Athanasios, significant portions of the original artwork remain recognizable. Researchers believe the artists employed sophisticated combinations of mineral, pigments, carefully prepared plaster surfaces, and controlled application techniques. Red pigments were likely derived from iron oxides, while black colours may have originated from carbon-based materials. White pigments probably came from lime compounds. The challenge is that modern scientists can identify many ingredients, but fully reproducing the exact durability of the original system remains difficult. The preparation of the wall itself may be even more important than the pigments. Microscopic studies indicate that multiple layers of plaster were applied before painting began, with each layer possessing specific physical properties designed to create a stable surface. The final result acted almost like a protective technological system, rather than a simple painted wall. The comparison with other ancient sites is striking. The famous wall paintings of Pompeii survived roughly 1,900 years before excavation, while the Agios Athanasios paintings are approximately 4 centuries older. Yet in some sections, their visual preservation remains surprisingly competitive. This suggests that Macedonian artists possessed highly advanced practical knowledge of materials science, even if they lacked modern chemistry. The most fascinating question is simple: how much of their knowledge has been lost? Ancient craftsmen left no technical manuals explaining every step of the process, and their expertise may have been transmitted through workshops and apprenticeships before disappearing forever. The tomb itself demonstrates impressive engineering capabilities. The structure consists of a long entrance passage leading to a burial chamber built with precisely cut stone blocks. After more than 2,300 years, major portions remain intact despite earthquakes, weathering, and human activity. Although the dimensions are not as massive as the pyramids of Egypt, the precision is remarkable. Builders had to excavate the site, transport heavy stone blocks, construct load-bearing walls, and create a stable underground environment capable of protecting valuable paintings and burial goods. One of the greatest engineering puzzles involves environmental control. Moisture is among the most destructive forces affecting ancient paintings, as excess humidity promotes biological growth and damages pigments, while temperature fluctuations create expansion and contraction within materials. Yet the tomb remained sealed for centuries while preserving much of its artwork. Archaeologists suspect that the structure's geometry, wall thickness, and burial depth may have unintentionally created a relatively stable microclimate. Whether this was deliberate engineering or fortunate design remains debated, but either way, the result demonstrates a sophisticated understanding of construction principles. The artistic quality visible at Agios Athanasios raises another question: who painted these images? The figures display accurate proportions, detailed clothing, realistic movement, and carefully planned compositions. Such work required years of training, yet, unlike many famous artists of later periods, the creators remain anonymous. Ancient literary sources frequently praise Greek painters such as Zeuxis and Apelles. Apelles, who worked during the age of Alexander the Great, was considered one of the greatest artists of antiquity. Unfortunately, none of his original paintings survive. Sites like Argos Athanasios therefore provide rare glimpses into the artistic traditions that once impressed the ancient world. The tomb suggests the existence of highly organized workshops capable of producing elite commissions. These workshops must have possessed specialized knowledge in pigment production, drawing techniques, surface preparation, and large-scale project management. Yet the details of how they operated remain largely unknown. Among the most valuable images are depictions of Macedonian soldiers. The warriors shown in the paintings carry equipment associated with the armies that transformed warfare under Philip II and Alexander the Great. Long spears, shields, armor, and ceremonial clothing appear throughout the artwork. These images provide rare visual evidence for one of history's most successful military systems. Alexander's empire eventually stretched from Greece to Egypt and as far east as northwestern India, covering millions of square kilometers. However, some artistic details differ from traditional reconstructions based on written sources. Certain equipment configurations remain debated among military historians. Were these differences artistic choices, regional variations, ceremonial uniforms, or evidence that modern reconstructions are incomplete? The paintings continue to fuel scholarly discussion. The owner of the tomb remains uncertain. The scale of the monument indicates tremendous wealth. Construction, decoration, and burial preparation required substantial resources, making such projects far beyond the reach of ordinary citizens. Some researchers propose that the occupant belonged to the highest levels of Macedonian society during the turbulent decades following Alexander's death. Others suggest connections to powerful noble families that governed portions of the kingdom during the successor wars. Without inscriptions clearly identifying the deceased, certainty remains impossible. The tomb preserves evidence of status and influence, but not the name itself. This creates one of archaeology's most frustrating mysteries: understanding the achievements of an individual whose identity has vanished. Argos Athanasios required remarkable coordination. Stone, plaster, and pigments had to be sourced and prepared, while artists, engineers, and laborers worked together under a unified plan. Without modern technology or machinery, the Macedonians still completed highly complex projects. The tomb suggests they possessed advanced organizational systems capable of managing resources, labor, and expertise on a large scale, even though the details remain unknown. How did Macedonian craftsmen develop artistic and material technologies so effective that their work continues to survive more than 2,300 years later, while much of the knowledge that created it has completely disappeared? Mitsero Red Lake is a blood-red lake in the hills of central Cyprus. Beneath its quiet surface lies evidence of one of the ancient world's great copper-producing regions. Thousands of years before modern geology, chemistry, and industrial mining, people here extracted and processed enormous quantities of copper ore using techniques that archaeologists still struggle to fully explain. The story began long before the modern lake existed. The red water visible today occupies an abandoned mining area near Mitsero, a region rich in copper sulfides. Archaeological investigations conducted throughout the 20th century revealed that this landscape formed part of the vast copper industry that made Cyprus one of the most important metal suppliers in the Bronze Age Mediterranean. Excavations uncovered ancient mining debris, slag deposits, smelting remains, and evidence of intensive metallurgical activity dating back more than 3,500 years. The first mystery is scale. During the Late Bronze Age, roughly between 1600 and 1100 BCE, Cyprus became one of the principal copper exporters in the Mediterranean world. Scientific isotope studies performed on copper artifacts discovered in Egypt, the Levant, Greece, and Anatolia indicate that a substantial portion of the metal originated from Cypriot ore deposits. This is remarkable because copper production was not a simple process. Ore had to be located, extracted, crushed, sorted, smelted, refined, cast into ingots, transported to ports, loaded onto ships, and distributed across international trade networks. The famous Uluburun shipwreck, discovered off the coast of Turkey, provides a striking example. Dating to around 1300 BCE, the vessel carried approximately 10 tons of copper ingots and 1 ton of tin. Many researchers believe a significant portion of that copper originated from Cyprus. To fill only one ship of that size required the extraction and processing of vast amounts of ore. Yet archaeologists still debate how Bronze Age societies organized enough labor to sustain production on such a massive scale. No written manuals survive, no detailed mining records exist, and the industrial system that powered Cyprus remains largely invisible. The greatest mystery surrounding Mitzro is not mining itself, but what happened after the ore left the ground. Most copper ore found in Cyprus is not pure metal. It commonly occurs as sulfide minerals mixed with large quantities of useless rock, and in many cases the concentration of copper within raw ore is relatively low. If ancient metallurgists attempted to smelt everything they excavated, they would waste enormous amounts of fuel and labour. Instead, evidence suggests they somehow improved ore quality before smelting. Modern mining calls this process ore beneficiation. Today, beneficiation involves crushing, grinding, density separation, flotation systems, magnetic sorting, and sophisticated chemical treatments. Ancient miners possessed none of these technologies, yet archaeological evidence indicates they achieved surprisingly effective results. The question is how. Researchers studying Bronze Age slag from Cyprus discovered that smelters often worked with ore that had already been enriched before entering furnaces. This suggests that waste rock had been removed earlier in the production chain. One possibility involves visual sorting. Experienced miners may have distinguished valuable ore by subtle differences in colour, texture, weight, and crystal structure. Copper minerals often display distinctive green, blue, red, or dark metallic appearances, and generations of practical knowledge may have allowed workers to identify profitable ore with remarkable accuracy. Another possibility involves density separation. Crushed ore could have been washed with water, allowing heavier mineral-rich fragments to settle while lighter waste material floated away. Similar principles were used in ancient gold mining and are still employed in modern mineral processing. Yet a major problem remains. No large-scale beneficiation installations have been conclusively identified around many Cypriot mining sites. Archaeologists see the results of enrichment but often cannot reconstruct the exact methods. The mystery becomes even more intriguing when compared with other ancient mining centres. At the Timna copper mines in southern Israel, extensive evidence of smelting survives, but ore quality varies significantly. In Serbia's prehistoric Rudna Glava mines, extraction techniques are visible, yet large-scale ore upgrading remains poorly understood. Cyprus appears to have operated on a larger scale than either region, while maintaining surprisingly efficient production. This raises a difficult question. Did Cypriot miners possess specialized ore processing knowledge that disappeared entirely from history? Some researchers argue that the answer may be yes. Unlike stone tools or furnaces, technical expertise leaves few traces. A master ore sorter could spend decades learning to identify profitable rock by sight alone, and such knowledge could vanish within a few generations if transmission stopped. What survives today may be only the final products, while the most important technology existed entirely inside human memory. Producing copper required enormous quantities of charcoal. Experimental archaeology suggests that generating a single kilogram of refined copper could consume many kilograms of wood, meaning that large-scale Bronze Age production would require immense forest resources. Yet environmental studies indicate that Cyprus retained significant woodland areas throughout much of its mining history. How was this possible? Some scholars propose carefully managed woodland harvesting. Others suggest furnace designs were more efficient than previously believed. A few researchers argue that ancient metallurgists optimized fuel consumption through advanced control of airflow and temperature. The exact answer remains uncertain. The copper deposits around Mitsaro are associated with complex volcanic formations known today as the Troodos or firelight. Modern geologists recognize this region as one of the world's most important exposed sections of ancient oceanic crust. But Bronze Age miners obviously had no geology textbooks. Nevertheless, they consistently located some of the richest ore bodies on the island. This pattern appears repeatedly across Cyprus. Mining activity often concentrated precisely where modern geological surveys identify economically valuable mineralization. How ancient prospectors accomplished this remains debated. Perhaps they recognized mineral stains on exposed rock, perhaps they observed unusual vegetation patterns, or perhaps they followed water chemistry or surface discoloration. Whatever the explanation, their success rate was remarkably high. Copper from Cyprus traveled hundreds and sometimes thousands of kilometers. Artifacts made from Cypriot metal have been identified across much of the eastern Mediterranean. Egyptian kingdoms, Mycenaean Greece, Levantine ports, and Anatolian powers all participated in the Bronze Age metal economy. Maintaining such a network required coordination on an extraordinary scale. Ore moved from mines to processing centers, metal moved from furnaces to workshops, ingots moved from inland production zones to coastal harbors, and ships moved cargo across dangerous seas. Yet no surviving administrative archive explains how the system functioned. The industrial machine is visible only through fragments, and the instructions have disappeared. That may be the greatest mystery of Mitsaro Red Lake. What do you think was the secret behind Cyprus's ancient copper industry? Forgotten practical expertise, an undiscovered processing technology, or something archaeologists have not yet found? Kleimonas is a prehistoric settlement on the southern coast of Cyprus that may hold one of the greatest unsolved technological mysteries of the Stone Age. How did people more than 10,000 years ago cross the open sea and bring an entire agricultural way of life to an island? The site of Kleimonas lies near modern Agios Tychonis on the island of Cyprus. Radiocarbon dating places the settlement between approximately 9,100 and 8,600 BC, making it one of the oldest farming communities ever discovered on a Mediterranean island. What makes Kleimonas extraordinary is not simply its age. The real mystery is that everything found there suggests the inhabitants did not arrive as primitive explorers. They arrived with crops, animals, construction knowledge, social organization, and a complete farming economy already in place. In many ways, Kleimonas appears less like the beginning of civilization, and more like the successful transplantation of an existing civilization across open water. The site was discovered during rescue excavations conducted by French archaeological teams beginning in 2009. Beneath layers of soil, researchers uncovered circular houses, storage facilities, tools, and most importantly, evidence of domesticated wheat. Radiocarbon analysis soon revealed dates older than nearly all previously known farming settlements on Mediterranean islands. The discovery immediately challenged long-standing theories regarding the spread of agriculture throughout the region. The greatest mystery surrounding Kleimonas concerns transportation. Cyprus has never been connected to the mainland during human history. Even during periods of lower sea levels, the island remained separated from the Levant by roughly 70 to 100 kilometers of open water. To reach it, prehistoric sailors had to navigate beyond the horizon. That alone would have been an extraordinary achievement. However, the inhabitants of Kleimonas appear to have transported much more than people. Archaeologists discovered remains of domesticated einkorn wheat, indicating that settlers deliberately carried cultivated crops from mainland Southwest Asia. Studies suggest that the wheat originated from regions associated with the earliest farming communities of the Fertile Crescent. The seeds had to survive long sea voyages and then be successfully planted in unfamiliar environments. The challenge becomes even greater when considering the logistics involved. A viable farming colony requires food reserves, breeding stock, tools, water containers, construction materials, and enough people to establish a stable population. Modern experimental archaeology has demonstrated that transporting even a small number of animals across open sea using primitive vessels is extremely difficult. Yet the settlers of Cleomenes accomplished something far more ambitious. The comparison is astonishing. The famous Viking voyages across the North Atlantic occurred around 1000 AD, roughly 10,000 years after Cleomenes was founded. Viking ships were built using iron tools, advanced woodworking techniques, and centuries of maritime experience. The people who settled Cleomenes possessed none of these advantages. No boats have survived, no harbours have been found, no written records exist, and the technology that enabled these voyages has completely vanished. Some archaeologists estimate that multiple successful crossings would have been necessary to establish a sustainable colony. A single voyage would not have transported enough people or resources. This implies the existence of repeated maritime operations centuries before the invention of sails as commonly understood. The result is one of the oldest and least understood examples of large-scale seafaring in human history. At the centre of Cleomenes stands another puzzle. Archaeologists uncovered a massive circular communal structure, approximately 10 meters in diameter. For a settlement dating to the PPNA period, this is an enormous building. Most houses measured only a few meters across. The central structure was significantly larger than ordinary dwellings and appears to have served a collective purpose. Constructing such a building required far more than simple labor. Workers had to excavate a large circular depression, stabilize its walls, erect supporting wooden frameworks, and create a roof spanning a considerable distance. Without metal tools, pulleys, or mathematical engineering, they managed to construct one of the earliest known public buildings on a Mediterranean island. The structure invites comparison with communal architecture at sites such as Jericho and Göbekli Tepe. Yet Cleomenes stands apart because it appears within an isolated island environment. How did a newly established island community organize enough labor and technical knowledge to construct such a building almost immediately after arrival? The village was not randomly placed. Excavations revealed that many structures were built on carefully prepared terraces cut into sloping terrain. These artificial platforms created stable surfaces for houses and communal facilities. Creating terraces may sound simple, but it involves understanding erosion, drainage, and load distribution. Even today, improperly constructed terraces often collapse after heavy rainfall. The inhabitants of Cleomenes lacked surveying instruments, metal shovels, and written engineering manuals. Nevertheless, they transformed uneven ground into a functional settlement. This achievement resembles landscape modifications seen in much later societies. In some respects, it anticipates techniques that would later become common in Bronze Age agricultural communities thousands of years afterward. How these early settlers acquired such practical engineering knowledge remains uncertain. Another overlooked mystery concerns construction materials. The buildings at Cleomenes were primarily made from earth and timber. Such materials are inherently fragile. Rain, erosion, and biological activity normally destroy them rapidly. Yet archaeologists were able to identify remarkably clear architectural traces after more than 10,000 years. This suggests that builders may have possessed sophisticated methods for selecting soils, controlling moisture, and reinforcing structural walls. Modern studies of ancient earthen architecture show that slight variations in clay composition can dramatically affect durability. Certain mixtures resist weathering far better than others. The people of Klimanars seem to have understood these properties through experience. Exactly how they prepared their construction materials remains unknown because the organic components have largely disappeared. The evidence from Klimanars indicates that agriculture did not gradually emerge on Cyprus. Instead, it appears to have arrived already functioning. The settlers cultivated domesticated wheat almost immediately after reaching the island. This raises difficult questions regarding knowledge transfer. Agriculture is not merely planting seeds. Successful farming requires understanding seasonal cycles, soil conditions, storage techniques, crop management, and risk mitigation. A failed harvest on an isolated island could have resulted in catastrophe, yet Klimanars survived. The community maintained agricultural production long enough to establish a stable settlement. Some researchers describe this as evidence of a highly organized colonization process, rather than spontaneous migration. The settlers may have planned their expansion carefully, carrying generations of accumulated agricultural knowledge across the sea. Perhaps the greatest mystery is social, rather than technological. Who coordinated all of this? Someone had to organize voyages, allocate labor, distribute resources, and decide where the village would be built. Yet there is no evidence of kings, governments, writing systems, or formal administration. The settlement demonstrates remarkable coordination without leaving behind obvious signs of centralized authority. This creates a paradox. The achievements visible at Klimanars suggest a level of planning comparable to much later societies, yet the conventional indicators of political organization are absent. Researchers continue debating whether leadership was temporary, communal, religious, or based on kinship networks. The truth remains unknown. Northern Armenia, above the deep gorges carved by the Dzoroge and Urat rivers, is home to the ruins of Lori Fortress. Built in 1065 by King David I of the Kingdom of Tashir Dzoroge, the site was known to historians long before systematic archaeological investigations began in the 20th century. Those investigations revealed something far more complex than a medieval stronghold. Beneath the ruins lay the remains of an entire mountain city that once supported nearly 10,000 inhabitants and contained engineering systems whose full sophistication remains difficult to explain today. The ruins occupy a plateau nearly 1,500 meters above sea level. Steep cliffs protect most sides of the settlement, transforming the surrounding landscape into a natural defensive barrier. Even now, standing on the edge of the fortress, it is easy to understand why the location was chosen. What remains difficult to understand is how medieval engineers transformed such an isolated mountaintop into a functioning urban centre capable of supporting thousands of inhabitants for centuries. The first mystery begins with the fortress itself. Most medieval fortresses were built on hills, but Lori was built on something closer to a natural stone island surrounded by enormous canyons. The plateau measures roughly 33 hectares, while cliffs on several sides drop hundreds of meters toward the rivers below. The location provided extraordinary protection, but it also created enormous engineering challenges. Every stone, every timber beam, every metal tool, and every kilogram of food had to be transported to the site. Modern military engineers recognize that logistics often determine whether a fortress succeeds or fails. During the construction of large European castles, transport routes were frequently as important as the defensive structures themselves. Yet Lori's builders selected one of the most inaccessible locations imaginable. Archaeologists still debate how construction materials were transported efficiently across such difficult terrain. The fortress walls stretch for approximately 200 meters across the most vulnerable approach, while natural barriers defend the remaining sides. The combination created a defensive system remarkably similar to principles used in modern military geography. What remains uncertain is the surveying process. The builders achieved an understanding of terrain that appears far more sophisticated than one might expect from an 11th century mountain kingdom. Without aerial photography, satellite imagery, GPS or modern maps, they identified a location that maximized visibility, defense and access to water simultaneously. The methods used to perform that survey remain largely unknown. Water has always been the greatest challenge for mountain fortresses. A fortress can survive without luxury, but it cannot survive without water. Researchers have identified evidence of sophisticated water infrastructure throughout Lorry. Archaeological investigations uncovered ceramic pipes, channels, reservoirs and components of a distribution system designed to support a substantial urban population. This raises a major question. How did engineers guarantee a stable water supply at an elevation of nearly 1,500 meters? Gravity-fed systems require precise calculations. Even a small error in gradient can stop water flow completely. Modern engineers use laser levels capable of millimeter accuracy, while medieval builders relied on simple instruments and experience. Yet Lorry appears to have maintained reliable water access for generations. The challenge becomes even greater when climate is considered. Northern Armenia experiences cold winters, seasonal rainfall variations, and periods of drought. A successful water system needed to function under all of these conditions. Comparisons with other medieval mountain fortresses reveal how unusual this achievement may have been. Many castles across Europe depended on wells drilled directly into bedrock, and some required shafts more than 100 meters deep. Lorry's engineers appear to have pursued a different strategy involving collection, storage and distribution. Parts of the system survive, but the complete design does not. One of the most surprising discoveries at Lorry involves public bathhouses. Archaeologists uncovered two major bath complexes containing multiple chambers, heating areas, ventilation systems, and water management features. These were not simple washing facilities, they represented significant engineering projects. The existence of advanced baths is itself remarkable. By the 11th century, many regions of Europe had abandoned the sophisticated bathing traditions associated with the Roman Empire. Yet Lorry maintained facilities incorporating concepts that resemble technologies used centuries earlier throughout the Byzantine world. Researchers identified evidence suggesting controlled airflow, temperature regulation, and water circulation. This creates an intriguing mystery. Where did the technical knowledge originate? Was it inherited through regional engineering traditions? Did Armenian builders adapt Byzantine concepts? Or did local craftsmen independently develop solutions optimized for mountain conditions? Some sections of the structures have survived for nearly 1,000 years, but the precise operating mechanisms remain only partially reconstructed. Historical sources indicate that bridges once connected the fortress to surrounding regions. Today, little remains beyond fragments and archaeological traces. The challenge faced by the builders was extraordinary. The river surrounding Lorry carved deep gorges through volcanic terrain. Crossing these natural barriers required structures capable of supporting military traffic, commercial transport, and daily movement. Bridge engineering has always represented one of humanity's most difficult technical challenges. Roman bridge builders relied on advanced stone arches, while medieval engineers often used timber systems vulnerable to weather and warfare. The exact designs used at Lorry remain uncertain. Researchers know bridges existed, but they do not know precisely how they were built. Questions remain about foundation techniques, load distribution, maintenance procedures, and structural lifespan. The missing bridges represent one of the largest gaps in our understanding of the fortress's infrastructure. Perhaps the greatest engineering mystery involves population. Historical estimates suggest that Lorry may have supported around 10,000 inhabitants during its peak. That number is significant. For comparison, many medieval European towns contained only a few thousand residents. Supporting a population of this size required food storage, waste management, transportation networks, workshops, markets, administrative facilities, and constant access to resources. Every urban system had to function simultaneously. Yet archaeologists have not identified enough surviving infrastructure to explain every aspect of daily life. Where were all the storage facilities? How was waste removed from such a constrained environment? How were supply chains maintained during military sieges? Researchers continue searching for answers. The fortress visible today may represent only part of the original city, and substantial sections could remain buried beneath centuries of collapse and sediment. The fortress was constructed primarily from local volcanic stone. At first glance, the masonry appears straightforward. Closer examination tells a different story. Builders had to quarry stone, shape blocks, transport them across difficult terrain, and assemble defensive walls capable of surviving earthquakes, warfare, and weather for nearly 1,000 years. Armenia sits within a seismically active region, meaning every structure faced long-term geological stress. Many sections of Lori still stand, despite centuries of earthquakes. Researchers continue studying how builders selected materials, distributed structural loads, and adapted construction techniques to local conditions. The answers could provide valuable insights into medieval engineering throughout the Caucasus. Brahmagiri in Karnataka, southern India, appears at first to be little more than a hill surrounded by ancient stone circles. Yet beneath its soil lies evidence of engineering knowledge, iron production, and construction techniques that continue to raise questions more than 2,000 years later. The site gained international attention in 1947 when British archaeologist Mortimer Wheeler conducted systematic excavations and uncovered extensive megalithic burials, iron artifacts, pottery, and evidence of a sophisticated society that flourished during the Iron Age of southern India. What archaeologists found was not merely a cemetery, it was a technological landscape. Among Brahmagiri's most striking features are its megalithic stone circles. Hundreds of stones were carefully arranged to mark burial chambers hidden beneath the ground. At first glance, the structures appear simple, but closer examination reveals something more intriguing. Many circles display surprisingly consistent geometries. The stones were positioned to create nearly symmetrical layouts, despite being constructed long before modern surveying instruments existed. Some circles measure several meters across and contain underground chambers built from massive stone slabs. Creating such layouts required more than brute force. Builders needed methods for measuring distances, maintaining alignment, and preserving circular shapes across uneven terrain. Modern engineers accomplish similar tasks using measuring tapes, transit levels, and digital surveying equipment, yet the people of Brahmagiri possessed none of these tools. Even so, they achieved results that remained recognizable for over 2 millennia. The question remains unanswered. What surveying methods allowed these ancient builders to organize large numbers of stones with such consistency? The burial chambers beneath the circles were constructed using large granite slabs, some weighing hundreds of kilograms and occasionally exceeding a ton. Transporting stones of this size presents a significant engineering challenge even today. Experiments conducted on megalithic construction elsewhere in the world suggest that moving a single 1-ton block may require dozens of workers operating in perfect coordination, with friction, terrain, weather conditions, and stability all becoming critical factors. Brahmagiri sits within a landscape dominated by rocky hills and granite outcrops. Extracting suitable slabs, transporting them across uneven ground, and positioning them with precision would have required extensive planning. No written instructions survive, and no ancient diagrams explain the process. like the builders of Stonehenge in Britain or the craters of the Moai statues on Easter Island, the people of Brahmagiri left behind the final product, but not the engineering manual. The burial chambers themselves represent another technological puzzle. Many consist of carefully fitted stone slabs arranged to create enclosed spaces capable of surviving thousands of years underground. These structures had to withstand soil pressure, seasonal moisture changes, and long-term geological stress. Modern archaeological studies indicate that some chambers remained remarkably intact despite centuries of environmental exposure. This durability suggests a practical understanding of structural stability. The builders knew which stones could support weight, how to position slabs to prevent collapse, and how to distribute loads without mortar or metal reinforcement. Yet none of this knowledge was recorded. The engineering principles survive only in stone. Perhaps the most important discoveries at Brahmagiri are the iron artifacts. Excavations revealed knives, spearheads, arrowheads, agricultural tools, and various iron objects dating to the early Iron Age. These finds demonstrate that the inhabitants possessed advanced metallurgical capabilities. Producing iron is far more difficult than producing copper. Copper melts at approximately 1085 degrees Celsius, while iron requires temperatures approaching 1200 degrees Celsius during bloomery production. Achieving such temperatures demands careful control of furnace design, airflow, fuel quality, and ore selection. Even slight mistakes can ruin an entire smelting operation. Experimental archaeologists attempting to recreate ancient iron production frequently encounter failures despite having access to modern scientific knowledge. Yet the metallurgists of Brahmagiri succeeded repeatedly, and their iron tools prove it. The mystery is not whether they understood metallurgy, the mystery is how they understood it so well. Of all Brahmagiri's mysteries, this may be the most fascinating. Ancient iron production was not a matter of simply heating rock until metal appeared. Every stage required precise, practical knowledge. The furnace needed the correct dimensions, the charcoal required specific burning properties, the ore needed suitable chemical composition, and the airflow had to remain within an effective range. Modern metallurgical analysis demonstrates that bloomery furnaces operate within surprisingly narrow performance windows. Too little oxygen prevents reduction of the ore, while too much oxygen oxidizes the metal and reduces quality. Ancient smiths had no thermometers, no pressure gauges, no chemical laboratories, and no written formulas, yet they consistently produced usable iron. This suggests the existence of an accumulated body of technical knowledge transmitted across generations. Some researchers compare this lost expertise to Roman concrete technology. The Romans produced marine concrete so durable that certain harbour structures have survived nearly 2,000 years of wave action, and modern scientists only recently began understanding the chemical processes responsible for its longevity. Brahmagiri presents a similar puzzle. The artifacts survive, but the knowledge does not. How did smiths determine the ideal charcoal-to-ore ratio? How did they recognize optimal furnace temperatures? How did they identify the best ore deposits without geological surveys? How did they train apprentices to reproduce successful results? Archaeologists can reconstruct parts of the process, but many operational details remain unknown. The formulas that once existed inside the minds of ancient metallurgists vanished long ago. What remains are the products of that knowledge. Technology does not emerge in isolation. The sophistication visible at Brahmagiri raises questions about how information moved across ancient India. Iron-working knowledge likely spread through networks of craftsmen, traders, and specialists operating over large distances. Yet no technical textbooks survive, and no instructional documents explain the transfer of metallurgical expertise. The situation resembles other ancient technological mysteries. The builders of the Egyptian pyramids moved millions of stone blocks, but left few detailed construction records. The creators of the Antikythera mechanism built an astronomical computer nearly 2,000 years ahead of its time, yet no instruction manual has ever been discovered. The inhabitants of Brahmagiri mastered iron production, but the educational system that supported that achievement remains invisible. The scale of Brahmagiri's megalithic landscape implies organized labor, constructing stone circles, quarrying slabs, building chambers, producing tools and conducting burial ceremonies required coordination among large groups of people. This suggests leadership structures capable of planning complex projects. Who directed these activities? Were there specialist engineers, professional stoneworkers, master metallurgists, or religious authorities controlling labor resources? The archaeological evidence provides hints but no definitive answers. The physical remains demonstrate organization, but the social mechanisms remain largely hidden. What do you think? Did the people of Brahmagiri possess technological knowledge far more advanced than historians currently recognize? Or are we simply underestimating the ingenuity of ancient engineering? Share your thoughts in the comments below.